Good morning and welcome to the RBCDSAI internal workshop on reinforcement learning. My name is Sridhar Kumar Narasimhan. I am with the Department of Chemical Engineering and associated with the Robert Bosch Center for Data Science and AI. After a colorful start to the weekend yesterday, we will now get a quick dive into the field of reinforcement learning over the next 3 hours. That we have So this is the rough agenda for today's morning session, or today's session in the morning. 9:30 to 10:30, we will have Professor Ravindran talk about reinforcement learning with structured actions and policies, followed by Ramya, who's a PhD scholar in the Department of Management Sciences here. We'll be talking on RL-based resource allocation for online experiments. Take a short break, give you some time to collect your thoughts and take a short break. If this were a physical conference, a physical event, I'm sure the center would have treated you to tea and snacks. Being hybrid, we'll all have a virtual coffee together. Then 11:10 to 11:35, we'll have Saarthak, dual degree student, talk about human in loop reinforcement learning, followed by Nishant, another dual degree student, talk about explainable reinforcement learning. And finally, to wrap up for the day, Utsav, who's an MS scholar, will talk about Thompson sampling approach to linearly constrained link adaption. With this, we'll quickly get onto the agenda. The first talk, I will introduce the speaker, Professor Ravindran. Professor D. Ravindran heads the Robert Bosch Center for Data Science and AI, which we fondly shorten in a short form called as RBCDSAI. RBCDSAI is one of the leading interdisciplinary AI research centers in India. Professor Ravindran is Mindtree Faculty Fellow and Professor in the Department of Computer Science and Engineering at Madras. He has held visiting positions at the Institute of Science in Bangalore, India, University of Technology, Sydney, Australia, and Google Research. Currently, his research interests are centered on learning from and through interactions and span areas of geometric deep learning and reinforcement learning. He's one of the founding executive committee members of the India chapter of ACM SIG KDD. He's currently serving on editorial boards of Machine Learning Journal, Journal of AI Research, ACM Transactions of Intelligent Systems and Technology, +1, Frontiers in Big Data and AI. It's published nearly 100 papers in premier journals and conferences. His work with students have won multiple Best Paper Awards, the most recent being the Best Application Paper at PAKDB 2021. He received his PhD from University of Massachusetts, and before that his master's degree in computer science from Indian Institute of Science, Bangalore. He's a senior member of the Association of Advancement of AI. This, I now hand over the floor to Professor Ravindran, and I'll stop sharing. And also, as a PSA, the session is being recorded. And I will, all question and answers, please use the Q&A box, which we'll be monitoring. And towards the end of the talk, we will, Professor, depending on how much time we have, we'll try to have Professor Ravindran answer that. Over to you, Ravi.
Thank you, Sridhar. And good morning to everyone. And I know that this is a slightly larger audience than we usually have for the internal workshops, but we felt that since online BSc students are also internal, so we should invite all of you to the workshop. So some of you are joining this for the first time. Welcome to RBCDSAI. Okay. And so today I'm going to talk about reinforcement learning with structured actions and policies. Just give me one sec. Hide everything. Great. So this is originally was meant as a talk to an audience that knows machine learning, but not necessarily familiar with the intricacies of reinforcement learning. But since this is a slightly broad audience, I'm going to give like a 2-slide introduction to what reinforcement learning is, but it's at a very conceptual level. So it would be hard for you to fully follow all the nitty-gritty details if you're not familiar with RL, but don't worry, I'll try to keep the talk at as high a level as possible. Right? So, I'm assuming that most of you are familiar with the usual notion of machine learning, right? Where you're given a lot of data, preferably with labels, So somebody says this is input, then you have to produce this as the output, right? And then from that you learn a function that can give an output for any new input that's given to you. But then if you think of how you learn to cycle, right? The cycling, I mean, you never learn from this kind of label data, right? Nobody tells you how to really cycle. They just tell you, hey, make sure you don't lose your balance, don't fall off, and things like that. But they don't tell you exactly how to do that, right? That you have to figure out through trial and error. That you know that falling down hurts, right? So you don't want to fall down, or if you do well, somebody will say, hey, well, good job, or something like that. So all these are the feedback that you're getting, right? So the crux that differentiates reinforcement learning from usual forms of learning from data is the following, right? Learning from data, somebody tells you upfront, here is the data, here is an input, and this is the output you should produce. And I do that for, a fixed set of inputs and outputs, and from that you learn a function. So somebody is giving you an instruction. This is the input, this is the output you have to produce, right? But in reinforcement learning, you try something, right? And then you get evaluated. You try to cycle. Then somebody tells you whether you did well or not. I mean, not meaning you fall down, right? So that is evaluation. So it comes post facto after you have taken an output. So that's crucially what differentiates reinforcement learning from usual forms of machine learning, right? So the whole the field of reinforcement learning is essentially this mathematical characterization of this learning from trial and error, learning through evaluation, learning through long-term feedback as opposed to immediate feedback, and so on and so forth. So that's basically what constitutes the field of reinforcement learning, right? And it's not just about cycling, right? If you think about it, naturally humans, babies learn to walk, they learn to talk, and so on and so forth through this kind of a trial and error process, right? Nobody really tells them how to form their vocal cords for speaking and so on. So here is a quick glimpse into how the abstraction would work. Normally, you think of a reinforcement learning agent as interacting closely with an environment, right? It will sense, what is the state of the environment. It will perform an action. It will apply it to the environment. So the state of the environment will be, okay, how much my cycle is, where am I on the road, how much my cycle is tilting by, how fast I am going, right? Are there pedestrians on the road and things like that. So all of this will be the input that goes to the agent. And the action would be, okay, now push down on the right pedal, push down on the left pedal, or go left, go right. So all of these would be the actions that the agent takes. And these actions are applied to the environment, which causes the environment to change, right? And this change could be in some kind of a non-deterministic fashion also. So there might be some small stone you didn't notice in the road, so you might wobble even though you are doing everything correctly and so on. Right? So that's the thing. And so this is the closed loop interaction. You also receive some kind of an evaluation, right, from the world. And this evaluation could be noisy. I mean, you might have done something wrong. For example, you are playing a game, right? You do a brilliant move, like in chess, right? You do a brilliant move that's going to cause the opponent to lose 4 moves down the line. But it's only 4 moves down the line, you'll know whether you have won or not, right? So the brilliant move does not immediately, get an evaluation unless you're playing in front of an audience and everybody goes, and you make that move. Okay. So other than that, you don't typically get that kind of evaluation. So the evaluation could be delayed. Right? So this is the setup that we're going to talk about, right? And the goal of the agent is to learn how to behave, right? How to take an action in response to a state, so as to maximize a measure of this, measure of this long-term evaluation, right? So usually RL people call this long evaluation as a reward, right? So I'll be using reward more often than I use evaluation. So the goal of the agent is to learn a mapping from states to action, which is called the policy, such that it maximizes this reward. Okay. So when I'm talking about taking some problem and forcing it as a reinforcement learning problem, I typically will have to think about these factors, right? So what are the states, right? Am I giving enough information to the agent to take decisions? So usually just looking at the world around you and just checking the raw inputs is not sufficient. You might want to do some processing on it, right? It just knowing that is a person in the immediate vicinity is not enough. You need to know if the person is moving towards the cycle or moving away from the cycle, for example. So those kinds of processing needs to be done to make it into information, right? Just the raw input is not enough. You need the signal that's enough for you to take decisions, right? The second thing you have to worry about is what are the actions? Right? What are the things that I can control? What are the things I can't control, right? So it could be discrete, right? It could be like moves in a game, like in chess, or it could be some items to recommend in some recommended system, or it could be continuous, right? It could be like a torque to a motor, or how much do I push the pedal by, the force with which I press something, right? That could be anything. And the whole talk is actually going to be about, taking a deeper look into what could these actions be, right? So, and looking at more structure that comes into the action. So normally the plain vanilla form of RL just talks about actions coming from a set or an interval. I'll come to that in the next slide, right? And finally, you have to worry about what the rewards are, right? They have to define the goal of the problem. It should not be something, that rewards you for doing frivolous things. So in situations like games, it's rather easy. Okay, I have to set a reward so that I win the game. But in other kinds of more complex control problems, it's not always clear how the reward would be defined so as to capture the goals of the problem, right? So, and that itself is a pretty active area of research, not just in reinforcement learning, in other aligned areas as well, right? Okay, so moving on. So everyone is interested in reinforcement learning nowadays because reinforcement learning is extraordinarily successful, right? Recent times. Forget about game playing, right? So it's even used in more complex control problems. It's used in controlling robots. It's used in controlling power systems. Like this is a graph from Google power data center power consumption. With reinforcement learning, it consumes 40% less. And more recently, RL has been impacting how people do science. So one of the big stories come out last year was on how RL can help people do protein folding, right, more effectively, and predict the 3D structure of proteins, and that in turn allows you to predict what the functions of the proteins would be, right? And so that is amazing. But now people have gone beyond that. They are using it reinforcement learning in augmenting chemistry, reinforcement learning in controlling nuclear reactions. All kinds of advances are now happening with AI and science driven by reinforcement learning. Now, since it works a lot, so there's a lot of attention being paid to it. And in this talk, I'm going to talk about a specific area that we have been working on, right? A specific direction of research that we have been working on at my group and at the center over the past few years, right? So the problem I'm tackling is this, right? Most reinforcement learning settings, like I said, assume the actions are from some kind of an unordered set. Like it could be joystick controls in a video game, or it could be directions north, south, east, west in a robot control problem, or some kind of fixed set of actions like pick, place, and grasp. And I'm calling these as unordered because there is nothing like, okay, this is the lowest action, this is the largest action, or anything, right? Or it could come from a real interval. So either actions are coming from some kind of unordered set, or they're coming from a real interval. It could be like joint torques, right? That the controls you're giving to a motor. It could be accelerations. It could be orientations. It could be continuous theta heading, right? And or it could be like a target location in an XY plane. I give you some real coordinates and things like that. So there could be a variety of such control actions that come from some kind of an interval, right? But then in many real world problems, right? So you actually have some kind of a structure, right? So it's often not just a question of even joystick controls, right? I could think of it as consisting of two components. That's a movement component and a firing component, right? So instead of treating it like 18 actions like they do in some of the reinforcement learning solutions, right, where fire plus move up is one action and move up is another completely distinct action, right? But in reality, they share something, right? They share the movement component, only the fire or not fire component of the action varies, right? So there could be this kind of a combinatorial action space. That could be, so you're selecting various, maybe Boolean variables also. This is present, this is not present. And like that, you have 10 different things that you want to pick, right? So you could have a combinatorial action space. So that's one kind of structure, right? That could be relational structure, right? Spatial locations itself, right? So instead of just thinking them as unrelated points in space, you could think of them as above, below, right? To the left of, to the right of. So there are these kinds of relational actions that you could think of, right? Or you could think of the whole action space being represented as a graph. And in fact, I'll show you examples of both of these when in the rest of the talk, right? And then there could be some kind of repeated structure in the action space. It could be that just a single action is repeated multiple times. So you don't just learn to go up, you learn to go up 5 times, right? Or so that is both the direction and the repetition that you need to learn, right? So that is one kind of structure for the action that we can try and capture, right? And otherwise, there is this whole notion of solutions getting repeated across tasks, right? So is there a way to take advantage of the fact that there are sub policies, right, that I can use across tasks, right? And so that is another way of thinking of this structure, right? And finally, my favorite is looking at what's called hierarchies, right? So I'll talk about hierarchies in more detail as we go along, but it's at a very simple level. You can think of it as follows, right? So whenever we try to solve a complex problem, so for example, you want to get from wherever you are, let's say you want to get to IIT campus. Let's say you are in Bangalore and you want to come to IIT campus. So how would you think about it, right? You're going to say, oh, okay, first I somehow need to get to Madras. Okay, if I'm going to go by the app, let's say I go to the airport, take a flight and go to Madras. And then I'll take a cab from the Madras airport and then I'll go to IIT campus and then walk to RBCDSAI, whatever, right? But now if you think about it, each one of these components that you came up in the solution itself is another problem. Okay, how do I go to the airport in Bangalore? That's an unsolvable problem, right? So it might take you several days to go from your home to the airport in Bangalore, right? But then you have to have a policy for doing that, right? And then you have to figure out how to book a flight and board the flight. So each one of these is a lot of nitty-gritty details that have to be solved for you to actually execute this solution that we came up with, right? But we don't think of it in that level when we are trying to solve the problem, because we start thinking of it at that level at the very beginning, you'll never come up with a solution. It just gets too complicated. So this is what I mean by hierarchies. You solve the problem at some granularity, and then you slowly, you reduce the granularity of the problem, and so that you can have a comprehensive solution to it, right? So I'll talk about hierarchies in more detail as we go along, but it's a very, very powerful abstraction tool, and a lot of work that I have been doing over the past years has been on trying to define hierarchical RL more and more. Okay. So I saw that somebody had put their hand up. I would request people to hold the questions till the end. If you have any questions, please put them in the Q&A box and we'll get to it at the end, right? So in fact, I won't be able to answer any questions along the way because I've closed all the boxes. So I don't know if you are posing questions now. I'll look at it at the end. I'll try to answer as many as possible. Okay. So in this talk, I'm going to talk about 4 different ways in which we are looked at structure. So one is what I call action repetition. So I'll talk about that. And then on action representation learning, right? So now if you start talking about actions that are related to one another, right? Instead of an unordered set, I'm going to have a set of related actions. We talked about that, right? Then you can start thinking about learning a representation for the action. Just like quite often people learn a representation for images, right? And then try to do some classification problems on it. You could learn a representation for. Typically, people talk about learning representation for the state alone because that is the input. They don't talk about learning representations for the output side, right, which is the action, right? So we argue that, hey, look, action representation learning is a very powerful generalization tool that we should explore. So that's the second set of things I'm going to talk about. And finally, I'll talk about combining pre-learned policies. I was telling you about how that could be notions of transfer from one earlier problem to a new problem. Right. So I'll talk about a little bit about various ways in which we have thought of combining pre-learned policies, right? Or also, learning a combination of policies also, not just combining pre-learned policies. Finally, if time permits, I'll talk about some work that we have been doing in collaboration with partners at UT Dallas and Oregon State, which we're pretty excited about, combining hierarchical planning and learning. But if I don't get to that, and I'll then, there are talks of this on the web that Harsha has given, and you can listen to those later, right? So I'll see. I'll certainly try to get through the first 3 parts, and the 4th one we'll see. Okay. So I have to acknowledge all the wonderful collaborators, a lot of students who work with me. Most of these are master students: Sahil, Arvind, Jana, Prasanna, Harsha, Priyesh, Rohan, Arjun, Rahul, Arvind, and Kevin. And a bunch of amazing collaborators. Brian, who was at Harvard as a PhD student and now is joining CMU as faculty. Liz, who was a grad student at Harvard and will soon be graduating. And Harsha, who is a PhD student at UT Dallas. And some wonderful collaborators, one both here and elsewhere. So Mitesh, who is a colleague at ITM, Sriram from Dallas, Milind, who is at Harvard and Google, Prasad at Oregon State, and Bharat Kaul, who is at Intel. Right? And of course, the work has been funded by multiple people. So Bosch, who fund the center, Google, Intel, and various other things. Okay, good. So first, I'll talk about repeated action, right? So this is some work that we did, Sahil and Arvind and I did back in 2017, and it came up with a model called Cigar, right? Fine-grained action repetition for deep RL. So the idea here is that we are deciding not just what is the action you want to take, but also how long you want to execute it, right? Because typically, you know, in human decision making, we don't change policies unless we really have to change something. So we don't keep vibrating our actions. We try to see as much as possible, you know, how few changes can we make to the policy that we are doing, unless it's absolutely warranted, right? So that's one motivation for it. And we also looked at, you know, what was happening in some simple domains like this, like video game playing domain, right? So here the goal is to get from the bottom of the screen to the top of the screen, right? So, and it turns out that the optimal solution consists of same action repeated multiple times. Here, this is an extreme case, right? It go up action repeated like 29 times. I mean, here, where you have a more complex dynamics, where you have to swim and rescue people and kill enemies, etc. in this game, you still have to do things like, okay, go down and keep firing. That's the combined action. Down and fire, you have to do that 9 times. Now go down left and fire 9 times. So this is, I'm sorry, this is just X. The fire is when you have the lightning bolt. So just go down 9 steps, go down and left 9 steps, and so on and so forth. So optimal policy consists of these kinds of large repetitions in many tasks. And even when you're navigating, so you typically tend to go up as much as possible before you turn right. Even though going like a staircase, go left, right, it could also be an optimal policy, right? It generally tend to, you know, go up all the way and then go right. Right? So all of these things led us to do this. And so we proposed Cigar. In fact, it's a very nice thing about Cigar is it is like a framework, right? It's like a wrapper algorithm, right? It can fit around any of this so-called deep reinforcement learning algorithms that are out there. And all you need to have is that it needs to maintain a policy explicitly. Right? Remember, I was telling you that the goal of the agent is to learn a policy. And if you have a parameterized representation for the policy, then you can implement Cigar around it, right? And so now we make a tweak to the whatever is objective function the original algorithm is using, right? And we add the action repetition also to it. And then it turns out that amazingly, in many of the Atari games that we tried, we got huge improvement. These are all percentage improvement over the best baseline that was there at that time. In some cases, we are getting like thousands of percentage improvement, right? And this is even without fully fine tuning for hyperparameters and playing for our approach, right? So it was like amazing. And what is more interesting is that in many of the games, you could see that the repetition was actually useful, right? So the way to interpret these figures is as follows, right? This is what fraction of the actions were repeated, right? So suppose I have a policy, I let me say take 1,000 actions to finish playing a game, right? So this would mean that say the 50% of those actions were not repeated much, like only 1 to 3 times. The 50% of the actions were repeated. So that's the way to interpret this. So the more pink, the deeper pink the bar is, right, the more the repetitions happened, right? So you can see that there is no one value of repetition that I could have picked a priori across all these games. And even within a game, right? Sometimes even though Freeway, a good fraction, right? Almost 20% of the actions were repeated like 30 times, right? But that doesn't mean that it is always good to repeat actions 30 times. Sometimes, like again, another 15% of the actions were repeated only 1 to 2 times. So it turns out that this is a great hyperparameter which you don't want to fix earlier, right? So we just put it into the optimization and we get significant improvement in performance. And as you saw in the previous slide also. Okay, good. So that's one thing. It's a very simple trick, and it turns out that they can add it to any you can add it to any reinforcement learning algorithm. So it actually is a very powerful trick to have. The next thing I want to talk about is this notion of action representation learning or action embedding, right? So typically reinforcement learning methods, right? So in fact, ironically, more classical methods can do well with a small set of actions or they can do well on actions that are coming from an interval, right? So, I mean, if you think of actions coming from an interval, that's literally an infinite number of actions. But if you go to continuous action space, you can do well. If you're in a small set of actions, you can do well. But if you have a large number of discrete actions, right, then RL methods have trouble, right? They have very difficulty generalizing, right? But typically, when you go to these kinds of large set of actions, right, large set of discrete actions, they are not truly disconnected discrete sets, right? I mean, if you think of them as items to recommend, right? So it will not truly be like a million items that are unconnected to one another. I mean, there will be categories over these items. There will be, producers like manufacturing brands, right? That will be common across some of these items. So there will be features of these items, even though I'm thinking of them as individual items that I have to recommend, right? So now it could be that, okay, am I recommending a soap versus am I recommending a shampoo, right? I mean, within soap, there might be a lot more action. So there is all kinds of structure in these kinds of actions, right? So instead of learning as a unordered set of hundreds of actions, you can actually choose actions in some kind of latent space, right? Just like some small number of variables that encode the action structure, right? So I talk about two examples that we did ourselves, and I also talk about one paper that kind of kicked off this whole action representation learning thing, right? So just like you do generalization on your input, now you do generalization on output on a parameterized setting. Right. So here is something that kicked off. So Yash Chandran, who actually was part of our group for about a year before he went off to do his PhD, came up with this idea of learning action representation. So here is a simple example. There is an agent that can navigate in one of these many directions and with different speed levels. So there are multiple speed settings, and depending on the actual setting of these control variables, right? You can basically end up in different parts of the work, right? You start from the middle, and then you can go this way, that way, and you can see that there are many possible outcomes of these actions. But then there are commonalities, right? It's like actions take you in one direction mostly. So what he did was he showed that, hey, instead of treating these as 2 power n actions, right? You could actually do this kind of representation learning, this E1 and E2 or some arbitrary vectors, right? On which you're projecting these action effects, right? And then you can say that, okay, I'm going to go in this green corner, which is blue corner, which is red and yellow corner and things like that. So basically you can learn to generalize over these as opposed to looking at these as just 2 power n elements in the set, right? Now we have made it part of a two-dimensional space, right? Then he showed that, hey, look, this is 2 power 8 actions. And without this kind of representation learning, you achieve only about 60% of the total return. While with this kind of representation learning, you are able to get much better, right? About 100% or close to 90% of the reward that you can get, you are getting, right? But now we go to something larger. Let's say you look at a problem with 2 power 12 actions. It turns out that your performance really sucks, right? And without learning these representations, and if you learn representation, you're doing really well, right? So you're getting close to 90% of the reward, right, that you could get. So this kind of motivated people to start looking at action representations a lot. In fact, independently, while Yash and his group are working on this action representation, we have also started exploring action representation learning here. And so we came up with some of these results, right? So here is one work which looked at RL for, looking at allocating resources in a patrolling scenario, and also doing something after that. But I'm more interested in the allocating resources part for this talk, because that is where we had to do this action representation learning. This is work by a whole bunch of people. So Arvind, Liz, Harsha, Keval, and of course, all of us were guided by Milind. This appeared in AMA's, one of the top multi-agent systems conference last year. Okay, so here is the problem. So there is this kind of forest setting, right? And there are animals in the forest roaming around, so we don't know exactly where they are right now, but we know the distribution of where the animals would be, right? Then there are people who could potentially come in and hunt the animals and go. They are poachers, right? And the goal was to figure out how to allocate rangers, who are like forest rangers, right, forest guards, and some drones, right, across this space, right, so that we can defend against these poachers who are coming in, right? So if the ranger encounters a poacher, then the ranger can arrest the poacher. Or if a drone encounters a poacher, it can signal to the ranger, or it can warn the poacher, and so that the poacher runs away, right? So it turns out that how well we do in terms of defending the territory depends a lot on where we decide to position the drones and the rangers, even though they still will be moving around and trying to cover the space. But where we start them off seems to have a significant effect in the how effective we are in defending against the poachers, right? So we decided to do this as a two-stage problem. First, we look at the allocation. So the allocation stages, okay, here is the world. Okay, there is some kind of animal density and other things that I have here, right? How do I allocate the rangers and the drones? And in response to the adversary being somewhere, right? I don't know exactly where the adversary is. I have to encounter the adversary during my patrolling to know where the adversary is, right? So I have to allocate them in such a way that regardless of how the adversary tries to come in, I'll have drones and rangers nearby to defend, right? And so there are a lot of grid cells, right? There are M cells potentially, right? And I have M agents, right? So in this case, I have 5 agents. So 2 rangers and 3 drones, right? So I basically have n choose M times M factorial ways in which I can position these defenders in these n cells, right? I pick M locations, and then I could put any one of the defender agent in any one of the locations I have picked. And then n choose M ways to pick these locations. It's a large number of actions. If I try to do any kind of optimization or reinforcement learning on top of this, it's just not going to work well, right? So the plain vanilla RL algorithms perform very poorly with these kinds of large discrete action spaces. So we basically learned an embedding, right? And so I just gave you motivation from wildlife poaching. We can use it in other kinds of resource allocation scenarios as well, right? So we generated about lots of random allocations, and then we learned a representation on it using what's called an autoencoder, right? And there are multiple ways in which you could have learned the representation. We just use this autoencoder to learn the embeddings. So basically, what will happen is for every position of drones and rangers and adversaries we put in, right? We get one vector as an action. So now the goal of the agent, instead of learning to choose from this n choose M times M factorial space, now becomes that you have to choose one of these k representative embeddings that we want to pick, right? So instead of looking at, okay, can I move the drone up by 1 square or down by 1 square and all that, so we don't make those fine-grained allocations. So we just pick k well-distributed actions, allocations, and then learn to choose from one of those. And so that's that. And then we combine that with the learning stage, and you can see that even though this is something that doesn't do that RL, whatever the action representation learning based allocation, that was the best before this. And now when we do the more clever allocation, right, we are able to get much better performance than the existing. So that's one thing that we did. And the second representation learning paper was on influence maximization in unknown social networks, right? And so here the idea is that I don't know the graph or the network of interactions. I mean, if you think of Facebook or LinkedIn as a social network, you kind of have APIs by which you can recover these, right? But we were operating in a domain where we're talking about real people interacting on the street, like homeless youth, right, or women in villages who are not likely to be on online social media, right? So we are talking about how they interact with one another. Typically, you end up having to interview people to figure out, who knows who, and then to construct a network of interactions by doing physical interview, right? These are pretty time consuming. So we'd really like to do something more efficient, right? In terms of how am I going to discover the structure of the network before I find out who are the influencers on this network. So again, this is worked with Harsha, Priyesh, and Bren, and with again Garrett Bimmelin. This ended up being the best paper runner-up, unfortunately, at AMAS 2020. Right. So So the idea here is that the abstract, the mathematical abstraction is that I give you a graph, right? And you have to select k nodes from this graph to activate, such that the information flows across the edge is maximized. Right? I start with k nodes. I start them with they are active, and then they can so start influencing their neighbors, and they can then influence their neighbors, and so on and so forth. And the idea here is that given a graph G, I know how to do this. Right? There are many heuristics, many methods for finding out how to select those top k nodes. But then what happens if I don't know the graph G, right? So what I do is I start off with some few people that I know are in the graph, right? And then I go through a network discovery phase where I query the nodes to discover which parts of the graph is connected, right? So basically, I don't know who else is there in the graph. I have to go ahead and discover the graph. Once I have the graph in hand, then I can run all this algorithms to pick out what the top k nodes are. Right? So we treated this as a reinforcement learning problem. Not the picking the top k nodes, even though that could also be modeled as RL. We didn't do that because there are very efficient algorithms for doing that. But the network discovery part, we treated that as a reinforcement learning problem. Right? So here, remember I told you had no states, actions, and rewards. So what are the states here? The states are basically how much of the graph do I already know. Right? So what is the part of the graph that I know? That's the state. And the actions are all the nodes that I know in the graph that haven't been queried yet. I haven't looked at them and asked them, hey, who are your neighbors? Right? I haven't asked them. So that's a set of actions. Okay. But notice that as I discover more and more of the graph, more and more of the action is also available to me. Because once I ask somebody and they tell me there are 4 more neighbors, then I can go and query them also. Right. So the set of actions is not even known a priori. And these actions keep changing over time. And from one graph to the other, it's not even the same actions. Right? So it's actually a pretty challenging thing to learn a policy that will work on multiple graphs, right? So you have to think of how do you represent the state, but also you have to think of how do you represent the actions, right? And of course we have a reward in terms of how good the discovered graph was finally, right? So how well did I end up doing my influence maximization on that? So here is an example. So here is a graph. All the nodes and edges here are the full graph, which you don't know to begin with, right? So what you know are the ones that are colored, right? The red ones and the gray ones are the ones that you know, and the red ones are the ones that you haven't queried yet. So they are potential actions for you, right? So the red and gray is your state. Together is your state, and the red alone are your potential actions, right? So now you select some node to query. So that is the node your RL agent selects to query. You query the neighbors. Now you get 3 more nodes, right? These 3 brown ones have been discovered, and this light brown is the one that you queried. So if you have not exhausted your query budget, now you accommodate this in your graph. So carefully look at what happens to the original graph. Now that has changed the state, right? So you've gotten all of these as new actions that you could potentially take, plus the old actions are already there. And now your graph has become known, right? More of your graph has become known than before, right? You keep doing this until you finish your query budget. If your query budget is finished, whatever you have seen so far, so everything in color here, right, becomes your final graph, and you run your influence maximization on it. So that's basically the thing, right? So the trick here was, okay, I have the state, which is a graph. I have to figure out how to represent the graph, but also the actions, right? So which are nodes of the network yet to be queried. They also need to be represented as vectors because A, they keep changing from one step to the other, and B, they're completely different from one graph to the other. So I basically have to look at, what is the average degree or some kind of information about that node, right, to represent it. And then I have to use those as action. So basically the setup that we did is this really complex neural network. But the way to think of it is the top pathway basically finds a representation for the state, and the bottom pathway finds a representation for the actions. And after this, we just feed it into a neural network and then get your final decision, right? So that's basically how we ended up implementing this. And then of course again, this is all percentage improvement. As long as the number here is greater than 0, right, we are doing better than the best algorithm that was out there, right? And like I said, so you have homeless, you have rural, and we also tried it on a couple of other networks. Okay. So we have about 15 minutes left. So let me see what I can do. So the third category of structure that I wanted to exploit, right? It's combining policies, right? So let's see. So remember I was telling you about hierarchical learning, right? So this is essentially how it looks like. So there is an observation, so state, right? It comes into something like a master policy, right? And then I have many of these sub policies. I mean, this could be about booking a ticket. This could be driving to the airport. This could be, opening the door of my house, whatever, right? So I have all of these sub solutions or sub policies that I have learned. And the master policy tells me, okay, which sub policy I'm going to do now. Okay, I want to first book a ticket. Okay, let me say book a ticket. And then what action do I actually perform, right? That changes the environment is going to come from the book a ticket policy, right? Or open the door, right? I could pick open the door, right? So then the actual action that I'm going to take is going to come from the open door policy. So there is this master policy, or if you will, higher level policy that learns across these sub policies, and each one of them actually learns to solve a separate subtask. Right? And in one particular hierarchical RL framework, these sub policies are called options. And this policy is like an inter-option policy, which decides, which option to take at which point. Right? That's the basic setup. So at a very high level. So one algorithm that one architecture that we came up, which is pretty, it generalizes beyond the notion of options also, right? It's more on the transfer learning side of things. So we call it attend, adapt, and transfer. And the idea here is that, let's say, look at this game here, right? So you're playing a pong. It's like an approximation of tennis. So we decided that we will do this way, right? So like the forehand and the backhand kind of a thing. Right? So we train two policies, right? One which is an expert in the top half of the game, right? The other which is an expert in the bottom half of the screen. So if the ball is in the top half of the screen, one expert will take over. If the ball is in the bottom half of the screen, another expert will take over. So you can see that the red expert is the top expert and the blue expert is the bottom expert. As soon as the ball goes to the top half of the screen, the red expert takes over, saying that this is attention you are paying to that. And then the ball comes to the bottom half, the blue expert takes over. And this is not pre-programmed by us. It is completely learned by using what is called an attention mechanism. So you can stack how many ever of these experts you want. Right? These are the green things here. And if you have more relevant experts, you learn very quickly, right? If you have only few of the relevant experts, you learn slowly. But then even if you have irrelevant experts, right? Like the red curve here, it starts off by doing badly, but very quickly it learns that the irrelevant experts should be ignored. And so irrelevant experts could be the things that are telling you to do the wrong things, right? So it quickly learns to ignore them and then switches to doing the right thing, right? So it's a pretty powerful framework. I'm not going to get into details of it, but here is another way where we took advantage of the structure. There are a lot of these experts which are good for small portions of the problem, and then we come up with a way to do this kind of a selective transfer, mix and match these experts so that we learn a better policy. Okay. Then the second way of looking at this, we looked at this approach called option encoder, right? It's kind of combines ideas from action representation learning as well as this kind of transfer that you looked at just now, right? So remember I was telling you these options are pre-trained, right? These sub policies were already learned, and there are many ways in which you can learn these sub policies, right? So there is a very popular algorithm called Eigen Options, and there's something called successor representation options or SR options that came from our group, and there are many such approaches, right? But the problem is that they learn a lot of options, right? Even though there might be only like 5 or 6 useful subtasks, right? So for example, Eigen Options could end up learning hundreds of these subtasks because they learn very, very small variations on the same task. They learn it as another subtask, right? So only some of these are useful. So what we thought of, okay, can we take these, we run these automatic option discovery algorithms. They're going to give me like 50 options or 100 options or whatever it is. Can I distill that option set into a smaller set that is useful and also in some kind of a task agnostic way? That means that it is not just useful from coming from Bangalore to Chennai. It's useful for, let's say, going from Bangalore to anywhere or going from anywhere to anywhere, 2 cities in India, right? And it should be able to capture the different things that you have to do, right? in terms of what behaviors, whatever behaviors you want to try. Right? You might want to actually take the flight and come from Bangalore to Chennai, or you might want to drive down from Bangalore to Chennai. So it should be able to give you all this power in terms of the solution classes that you want to explore. Right? So what we did here was the following. So we assumed that the options were already learned, right? So there were like this architecture is only for distilling from 4 to 2. Okay, because if you have hundreds, you want to reduce it, then structure will look different, right? And so we use ideas from deep learning. I'm not going to get the part of it. And so basically to come up with, so from 4 policies here, we come up with 2 representations, and that are enough to kind of reconstruct as much of the 4 policies as we can. And then we basically learn a policy, right, that maps to these distilled policies, right? So then we use a to T framework, right? So that this is basically like the A to T structure that we had earlier. So instead of having all those experts, you'll have these distilled policies as experts, and then you'll have a network and then an attention mechanism that will learn how to combine these two. That's basically how we did it. And you can see this. So there were 16 possible expert policies, each taking you to one of these blue squares in this world, right? And so there is this existing policy distillation setting where it takes all these 16 policies and it kind of ends up producing just single policy. But our approach allows us to look at producing 1, 2, 3, 4, how many we want. And here we took the 16 policies and distilled them into 4 policies. And you can see that like naturally these things fell into groups. I mean, again, this came out of the training process. We didn't hand tune anything. So the distilled policy 1 took you to the room top right, bottom right, bottom left, top left, right? So basically, so it kind of grouped them into similar policies. And now each one of these is just a single choice. As opposed to having 16 choices now at the high level, I only have 4 choices, but they are sufficient for me to go to any one of the rooms that we would like to, right? And like that, we did this for multiple settings, and so we did. And you can see that with the distilled policies, we are able to learn much faster, right? And we are really not losing out in terms of the final performance that can be reached, because vanilla A to C means that I'm not making any assumptions about the structure. I'm just learning the whole thing, right? And that basically we're getting very similar performance to learning from scratch, and we're certainly doing better than using the original policy, which is the pink one. So I'm going a little fast, I know, but most of the time. And so we did this not just on that simple kind of grid worlds, but we also did it in worlds where you are going to get views like this, right? So where you're going to get continuous graphical views like this, and we are able to look at this. So it's like this eye room that we have, right? So the goal here is to go to one of these 4 corners, and it manages to segregate those 2 policies into 2 policies, and then learn better, right? So I have done this on multiple other settings. So here is the goal is there is a red target here, and we have to move your robot arm to reach to the target. And then we start with 16 policies that can go to 1, 2, 3, 4, the corners, up, down, left, and all that. So there are like 16 different expert policies going to different parts of the space that were trained. And then we distilled it down to a small number of policies. So when you do one policy, it's kind of left and mid-level, and then right and top. So it just does that. And then if you're doing 4 policies, again, you can see that it learns nicely to segregate the behaviors, right? So that's the nice thing about right? So the next thing I want to talk about is way of doing ensembling, right? I know some of you might have heard of things like bagging and boosting, where you take multiple solutions, right, and you combine them to provide a single solution, and somehow the single solution is much better than any one of the individual solutions. So this is joint work with Rohan and a team who are then at Intel, right? And so the idea here is that so I'm going to take like these 5 policies, right, and then combine them together and then try to do better than any one of those individual policies. But the challenge is, if I'm going to do this in a dumb way, right, I would basically have to train the whole agent 5 times, right? So what we did was we took advantage of some of the things that people had looked at, especially this notion of what's called cycling learning rates, right? You start off with a high learning rate, you make it low, then go back to high, make it low, go back to high, make it low, and things like that. So the idea is that, so if you look at a error surface, right here, this is a classification error surface, not RL error surface. You can see that there are a lot of optima, like dips in the error surface. Like typically, our goal is to find the global dip, right? But that is often very challenging. So what we do with the cyclic learning rates is that we are hoping that you start from somewhere, but you're going to reach multiple of these local optima at every one of these dips in the learning rate, right? And since each of these local optima is capturing something about the problem, right? That is why it is better than the neighbors. So hopefully putting all of those solutions together will do better than doing any one solution. So there's a version of this for classification called snapshot ensemble. We weren't aware of the snapshot ensemble paper when we did this work, but later on we could kind of relate to that, right? So there are multiple problems even after that, right? So now I have a way of generating these 5 policies, right? Or 10 policies, however I want to do it. Right? I use this kind of cyclic learning rates. Just suppose I had like a million training iterations, which you have here. I basically use this is 10 million. I use 2 million for each policy, generating each policy. So that's one part of it, right? But now that I have these 5 policies, how do I figure out which of these 5 policies should I use in the ensemble, right? So I kind of do a post facto policy selection stage, right? That is what was different in the serial framework than the earlier approaches, is that we do this post facto selection of these policies. Now, once I have selected these, say in this particular case, we use 3 out of the 5 policies, and then we see that we get much better performance, right, across a variety of domains as compared to some of the earlier approaches. Right? Almost all of these are different ways of doing ensembles, right? And Rainbow DQN just takes like 5 or 6, 7 different RL algorithms, combines them. Similarly with Sunrise and Simple and Curl. And you can see that even though we are not uniformly the best, we are pretty good. And in most of these games, we are doing much better than the state of the art. Right? So that is right. So in fact, Rainbow DQN is for a single node machine, right? Rainbow DQN probably was the state of that. And so we are not comparing against heavily distributed algorithms, right, which require a lot of compute. Mostly we're comparing it against single node approaches. Okay, and of course, I can show this video. That means I wouldn't have time at all to talk about the other one, but let's do this video. So you can see on the left-hand side is the ensemble created by Cyril. On the right-hand side is a single policy, right? So now I'm going to forward both of these. I'm going to forward both of these to the like a minute and 23 out, right? So you can see that the single agent is still trying to clear the board while Cyril is there, right? I mean, it's done. And in fact, it's going to clean up the board now and restart, while the single agent is still trying to clear the board, right? So you can see that the ensemble method, this is the best performing single agent, by the way. So the ensemble is way better than any of the single agent, even the best performing agent, and it is able to achieve multiple times the performance of any one of the single agent. Right? So you could see that here, each of the single agent is having only some level of performance, and then we try some random subsets of this. The final one is the subset that is selected through our optimization. So I'm going to have to skip this, unfortunately. So this is RepRel, which is integrating relational planning and reinforcement learning. This is work that was led by Harsha, who's a PhD student at UT Dallas, and Arjun also collaborated in this. And Sriram is a colleague from UT Dallas, and Prasad is from Oregon State. So there is this multi-generational thing here. Prasad was Sriram's PhD advisor, Sriram is Harsha and Arjun's advisor. Right. So unfortunately, it's a very interesting work, but I'm going to ask people to go look at Harsha's talks that are online. Okay. So my takeaway for everyone is that deep reinforcement learning has revived the excitement in this community, right? Really, a lot of work. You can see that the number of deep RL papers is going up exponentially. We still need to update this up to 2017. But still, there are many fundamental questions that need to be addressed, right? So a lot of things. I mean, one of the things I'm talking about how to take advantage of structure, right? But the goal is to move RL more to what I call omnivorous learning, right? Not just worry about this reward function, this evaluation you're getting, but see how much you can use all kinds of information that you can get, right? And bring it closer to how humans learn. So there are a bunch of papers that I spoke about or didn't speak about today, so you can look it up. And I want to very quickly talk about some of the other things that RBCDSAI does, because we do have a non-RBCDSAI audience, right? So we do a lot of events throughout the year, right? Just a sampler, like these kinds of workshops that you see now, but also multiple seminars, invited speakers, conferences, and other things. Right, so you're welcome. We'll be putting out calls, which certainly be inviting the online BSc people, but even for some of the other events, the calls are open. So you can be on the lookout for these. And for people who are in their third year of your undergraduation or the pre-final year of your undergraduation, the summer internship applications are open till the end of this month. Please take a look and apply if you would like to. And so we also have a very innovative program called the PostGrad Fellowship for people who have finished their undergrad, or masters also, right? And the idea here is that you get exposure to research. It's a 2-year fellowship. Typically, you are independent to work on a problem of your choice with faculty from here, right? And most people who are here either graduate and go to grad school. If they finish their postdoctoral fellowships and go to grad school to do their masters or PhD, or they end up going to some kind of a startup or a data science job, right? So this is there, and we also have a specific position for women, where we also look at mentoring by women experts, as well as some other additional funding for going to women in science or women in tech events. And of course, I need to talk about this. We have not just the postdoctoral fellowship, we have a very, very competitive postdoctoral fellowship. If somebody has a PhD looking for more further research opportunity, that's the direction. And with the online BSc program, right, we have launched a couple of very interesting fellowships called teaching fellowships, right? So you get to do part-time, you get to do research with RBCDSAI. On part-time, you work on building teaching material and being an instructor in the online BSc program that IIT Madras is running, right? So you're honing your teaching skills as well as take part in some exciting research. And so we have two versions of this, one which is at the postbaccalaureate level for exceptional masters or bachelor students with some amount of experience in teaching, or we also are inviting postdoctoral teaching fellows. This is for people again with a PhD degree and some experience in teaching and who are also interested in engaging in high quality research with RBCDSAI. So thank you. And you can look us up online and on social media and other things. And now we have 1 minute for questions. Happy to take them.
Thanks, Ravi. I really enjoyed the talk and gives me a lot of ideas. I'm going to bug you after sometime over the weekend or next week. Yeah, there are 4 questions in the Q&A box which have been raised. Do you want me to read them out, or would you be?
I finally found the Q&A box.
Pardon?
I finally found the Q&A box.
Oh, okay, fine.
Okay. The first question is there a characterization of the environment against which the repeated action algorithm is best suited? Great question, right? And the answer, unfortunately, is not it, right? But then there are some environments in which I can tell you it is not suited. So, for example, we ran this on a problem like getting a humanoid to walk, right? So getting the humanoid to walk, literally by definition, you can't repeat the actions. When you move one leg, then you have to move the other leg. Right? So you can't just keep moving one leg, 3 or 4 times, you're going to topple and fall. So the method worked, right? Cigar worked there also, but it took a long time to understand that none of the action repetitions available to it were useful, right? It had to go back to an action repetition of one. So basically I had to try, multiple things and then finally figure this out. Therefore, it does do that, but it just takes longer to get there, right? So that's not the great setting for us, right? So that's one thing. So you can talk about the environments in which it's not suited, where you have some prior knowledge about how the structure of the policy is. But the nice thing is, you can, I mean, it doesn't preclude non-repetition at all in the framework. If you're not sure whether repetition would help or not, you could still try Cigar. It will just tell you at the end of the optimization whether it helped or not. Right? Yes. Right. So Govind's other question is, in this influence maximization, I assume that the size of adjacency matrix also changes as we keep adding new nodes. Yeah. Yes, it is going to change. Not with every iteration, but with every episode. Right. So if I go from one, oh yeah, no, it will change with every iteration, because the graph is defined only over the nodes that I have seen. You remember I was showing you these red and gray nodes, and all the white nodes were unseen nodes, right? If you're thinking of an adjacency matrix representation, it is defined only over the red and gray nodes, not over the white nodes. But after one step, I'll have more red and gray nodes, and therefore the adjacency matrix size will change. And that is why we needed to have two pathways in the network, right? So we had a state representation learning, and we had an action representation learning. So that was designed in such a way that it can handle different size graphs. So we had to do it that way. Yeah, you're right. Vishwa has this question: if you have an environment in which we can make observation every 100 or 500 steps, we have to pick actions every time step. The states are also not predictable. How would you solve the problem using RL? What framework would you use? So you make an observation every 100 steps. So there is this whole idea about doing a partial observable control, right? So one possibility is that you have to see, if the states are, there has to be some kind of predictability about the states between the observations. The states are completely unpredictable between observations, then there's very little that you can do, right? So if there is some kind of predictability over these, the gaps between the observations, you could learn a policy that does best in terms of the expected trajectory that you're going to see between these transitions. Right? So there are ways of doing it. I mean, there are ways of treating this as a partially observable problem, and solution approaches for partial observable problems. You can, since you know how to get in touch with me, you can try catch me separately and we can talk about it. But it's possible to solve. But there is absolutely unpredictable randomness between the steps, then nothing can work. Right? Oh wow, okay. What happens if a person gets some urgent work and he has to return from the airport? Then how would the learning continue? Okay, that's taking the example too literally, but I'm assuming what you mean is, so I have a subtask that I've already solved. What happens if there is a contingency and I have to abort the subtask in between, right? Well, it depends on how you set up the learning. If your learning is set up too simplistically, saying that, okay, if you start a subtask, you have to finish the subtask, then it becomes a little bit of a challenge. For example, it's like taking the bus to go to the airport, right? It doesn't stop anywhere in between. So once you get in the bus, you have to get down at the airport, and then you'll have to figure out a way to come back, right? And but then if you allow this kind of uncertainty even in that space, right? So your higher level, your meta learning agent, right? Remember I was telling you there's something that learns to switch between different options and things like that. That can still learn to accommodate this kinds of failures or this kind of replanning that needs to happen. So yeah, the hierarchical level framework is sufficiently powerful to accommodate all such variations, right? So we really need to let Ramya go. So I'll stop here. And thank you.
Thanks, Ravi. And I'm sure if there are other questions, I encourage them to ping you directly.
Yeah, well, I'm going to hang around. So if you want to put some questions on the Q&A bar for the next half hour or so, I'll be happy to answer.
Yeah, sure. Yeah, thanks. Thanks, Ravi, for that very interesting talk. And the next speaker we have is Ramya Chandran, who is a PhD student in the Department of Management Sciences. The research work primarily focuses on deriving experimental plans for online experiments using RL techniques. And the title of her talk is RL-based resource allocation for multiphase finite horizon experiments. Thanks, Ravi, and over to you, Ramya.
Yes,
I guess Ravi will have to stop sharing so that.
Yes.
I don't know what is happening because it says that I'm not sharing.
Oh.
I have to stop sharing because it says The only button I have is new share.
Okay.
Let me click on
I'll stop sharing, sir.
Yeah,
I'll
can you
stop you
stop
sharing.
it?
Yeah.
Can you
Yeah.
stop it? Yeah. Because the button has gone away from my screen. Yeah, thanks.
Are you able to see my screen, sir?
Yes, you may want to do Control L or full screen.
Yeah, sure. So good morning, everyone present here. I am Ramya Chandran, and I'm working on the project that using reinforcement learning based resource allocation for multiphase finite arrays on online experiments. And this work was guided by Professor Nandan Sudarshanam. So generally, if you take experiments, the experiments are conducted in order to gain knowledge about any particular system. The accuracy of the information or the knowledge gained through experiments goes up with the size of the experiment. On the other hand, as the size of the experiment increases, the cost of conducting the experiment also increases. So there is a trade-off between the accuracy of the knowledge gain and the cost of conducting the experiment. So in such cases, there is what amount of resources to be allocated for the experiment becomes a prominent question. And this question becomes more prominent when under two scenarios. One, when the experiment has the resource available for the experiment is limited, and in another framework where the experiments are conducted in an online setting, by which I mean that the end products, whatever come out from the experiment, reaches the customers directly. So in this research, what we are trying to do is to study about the experimental designs, which is used for allocating the resources for such experiments, which are carried in an online setting, and where the resources available for the experiments is limited. So generally, the experimental design approaches can be broadly classified into two categories. So one being the based on the nature of the requirement, one being the adaptive structure, another one being the non-adaptive structure. So traditional multi-factor design of experiments is an example of a non-adaptive structure. For example, consider now an experiment where we have to choose the best alternative among a number of alternatives which is given. So in such cases, in the traditional multi-factor design of experiments, what they do is that, so all the alternatives are tried parallelly, and at the end of the experimental phase, the best alternative is chosen based on the results observed from the experiments. On the other hand, the adaptive or the sequential designs, a multi-arm banded framework can be an typical example for such adaptive designs, where actually after every trial, their decision has to be made with, onto which alternative to be chosen, and this decision is mainly based on the kind of feedback which you've received on your previous trials. So having said that, the traditional design of experiment framework are more useful in an offline setting, while like when the experiments are carried out in an offline setting, while the MAB framework mostly suits for experiments in an online setting. But though the MAB framework is more suited for online experimental thing, there are few online experiments which actually can be only conducted in parallel. For example, there are experiments which has some delayed response. For example, the social studies research or the policy research, which takes the response of the experiments takes time. So in such cases, and in certain other cases where the experiments, the immediate switching between the alternatives after each trial is not possible. For example, in a manufacturing setup, now say you're trying to find the optimal feed for a CNC turning machine or something like that. After every trial, changing the feed becomes cumbersome. So in such cases, we need to have a trade-off between the adaptive and the non-adaptive framework. So in this case, we go on with the semi-adaptive structure. We discuss the experiments with the semi-adaptive structure, and this usually the semi-adaptive structure experiments are conducted in multiple phases. So what are the advantages of the semi-adaptive structure when compared to a non-adaptive or an adaptive structure is that, so since experiments are conducted in parallel, in phases, each phase can be executed parallelly. and the overall time is reduced as compared to as a sequential design approach. And on the other hand, as we are conducting the experiment in phases, the results, whatever which is obtained in the previous phase, can in some form be incorporated as a prior knowledge to the next phase. So which is not generally there with the traditional design of experiment setting. So we find that the semi-adaptive structures kind of the experiments which uses the semi-adaptive structure to be more beneficial than the other two frameworks. So to get a more clear picture, now consider an experiment with a finite horizon. So where say the number of trials here, since we are seeing the experiment with limited number of trials, say the number of trials which is there, the resource available is T, and P be the number of phases in which the experiment is deployed in. So when P is equal to 2, then it becomes a typical parallel setting, like the traditional DOE framework. And when P is equal to T, it becomes more like a sequential framework, where on every trial we have to make a decision on which alternative to choose. So our research primarily focuses on generating experimental plans for the kind of experiments where the phase is in between 2 and T. So in our framework, we allow the experimenter to choose the number of phases in which he wants to deploy the experiment, and based on the number of phases chosen by the experimenter, we actually suggest an optimal resource allocation strategy. So a typical example can be in the clinical trials field, where actually the experiments are generally conducted in stages. So a typical two-stage structure will contain the pilot studies and the main trials. The pilot studies in some cases is again divided into more phases, like the internal and external, and the main trials in some cases again is divided into the phase 1, phase 2, and phase 3 trials. So here the experiments are supposed to be conducted in an online fashion, because any treatment or drug, whatever we use, directly reach the customer, the patient. So it fits in our framework, and it happens in a stage-wise manner, and so this could be a perfect example for a framework. So now dealing more with the problem setup, we consider a simple problem where the number of treatments or the arms is considered to be 2, and the distribution between the gap of the arms is considered to be a normal distribution with mean 0 and the variance sigma m square, and the noise associated in the system is also assumed to be taking a normal distribution with mean 0 and variance sigma e, and the total number of units which is found is T, and the number of phases which we are trying to deal with is greater than 2, as I said. And the metric used here is cumulative regret, which is generally used in many RL frameworks. So when T is equal to 2, this problem becomes a typical parallel setting problem, where the first phase does the exploration and the second phase does the exploitation. For a typical two-phase fixed horizon resource allocation problem, a closed form solution is proposed theoretically by theoretically in the paper Nandan et al. And here they use the metric cumulative regret, which is nothing but the sum of the exploration phases regret and the exploitation phases regret. So assuming that there's no prior knowledge, in the exploration phase, we allocate equal number of resources to both the treatments, and hence here say n number of trials are allocated to each treatment. So the regret in the first phase is n number of trials which is allocated to the suboptimal treatment into R, where R is nothing but the regret accumulated. That's nothing but the difference in the means of the two treatments, the optimal and the suboptimal treatment at each trial. And T minus 2n is nothing but the number of resources which is left after the exploration phase for exploitation. And this term gives the probability of choosing the suboptimal arm in the exploitation phase and into R. So this overall gives the regret, the cumulative regret for the T trial. On solving this equation, we can find the optimal n. So, but when we consider in our framework, like where we are trying to propose for number of phases which is greater than 2, there will be multiple possible scenarios for us to evaluate. So in such cases, such a theoretical framework cannot be extended. So instead, a brute force simulation technique can be used, where all the treatments can be tried, like all the possible combinations. So now say phases 3, so there will be n number of resources allocated to phase 1, and n1 and n2 number of phases allocated to the phase 2. So there will be a lot of combinations which we need to try in. And in this brute force simulation approach, what we do is we actually, what one can do is, for each possible combinations, you can try simulating the cumulative regret, and you can take the expectation over that and find the treatment which has the minimum expected cumulative regret. So what is the drawback in this framework is that as the number of phases increases, the number of combinations which we have to try is also increases. So in order to combat all the problems proposed, so we in this research, we are trying to model this problem using a Markov decision process, and obtain the solution for the problem using some of the RL techniques. So model formulation, as I said before, we are trying to model this as a Markov decision process, and the Markov decision process actually has 4 elements. One is the state space, action space, the transition property, and the reward distribution. Here in our problem, the state space consists of 3. We have defined the state space to consist of 3 parameters. One is the distribution of the 2 arms. So that is one parameter. The other parameter is the phase in which the state is currently in, and the other parameter is the number of remaining units at that particular phase. So, and then the action space, we have modeled it by using a tuple where of 2 proportions, where if n1 at a particular state, if n1 is the amount of resources allocated to the treatment 1, and n2 is the amount of resources which is allocated to the treatment 2, then the first proportion says what percentage of the resources is shared by both the arms, and the second proportion says what is the total amount of resources which is allocated to the particular phase given the total resource available at that particular phase. So usually the n1 can take values between 0 and t, and n2 can take values between 0 and t minus 1. T minus n1. So, and then the transition probability is nothing but at what probability at a given state, if you take an action A, what is the probability of moving to another state? So that's what defines the transition probability. And in this case, the state space consists of 3 parameters, out of which the number of remaining trials and the phase number is quite deterministic. Once you have you know what action you have selected in that particular state. So the only stochastic thing is the distribution of the arms. So that depends upon the feedback, which is the feedback or the samples received from the environment, based on which you update the distribution parameters. So, and then the reward distribution, to speak about the reward distribution, actually reward distribution is nothing but the regret, as I already mentioned. And regret in this case is nothing but the difference between the optimal and the suboptimal arm. The means of the optimal and the suboptimal arm. Let x1 be the true mean. It is sample from the prior distribution of the state for the arm 1, and x2 be the sample which is taken from the prior distribution for arm 2. And so the difference in some sense gives the regret. If the state is not terminal, and if x1 is greater than x2, then this regret is multiplied with n2, while the state is not terminal, and if x2 is greater than x1, then it is multiplied with n1, which means we are multiplying with the number of resources allocated to the suboptimal treatment. And if phase is terminal, we check whether the decision made in the terminal phase for the exploitation phase is correct or not. If it is correct, then there won't be any regret accumulated for that phase. But if the decision is wrong, then with some probability the decision might be wrong in some cases, where the regret is given by multiplying this term with the total number of resources which is there in the exploitation phase. So having modeled the MDP, now to obtain a policy, we actually use the algorithm, and this we propose an algorithm. Here actually we have divided this algorithm into two setups. One is the agent, another one is the environment. So first, to start with, the algorithm for the agent. So here we have used a Q-learning agent. And the interaction, by the nature of the problem, the interaction between the agent and the environment is episodic, and the length of each episode is nothing but equivalent to the number of phases, which was actually planned by the experimenter. So the inputs to the algorithm is the sigma m, sigma e, t, that's nothing but the total number of resources available, and p, which is the number of phases, and e is the number of episodes, and learning rate and the discount factor. So we initialize the queue, and then we start the episodic task. At each episode, we actually set the state to an initial phase. So here, when we set the state, we keep t to be t, which is nothing but the total number of units available, and p to be 1, because that's the initial state. And we set the distribution means to be 0, assuming that we don't have any knowledge before the experiment starts. So so having that as a state, and then we select an action by using the epsilon greedy policy, and we obtain the next state and the reward by from the environment, and we update the q value function, and we set the next state to be the current state, and go on until the phase reaches the terminal phase. And we follow this approach for so we follow this approach until we reach the number of episode to be, and the algorithm returns a value q. So this q, the q value function gives the optimal allocation and the optimal allocation, that's the action for each state. So how the environment works. So for the inputs for the environment is the state and the action. Now the state consists of, as I told, the state consists of the information about the distribution of the true means of the two arms. Here, two alternatives, whatever considered. So here, what we do is we actually sample one true mean from at each simulation. We actually sample one true mean from the distribution, and then we calculate what the n1 n2 should be from the fractions what discussed for the action space, and we actually get the true mean estimates by using the sampling distributions of the true mean, and then we update the prior. So this estimate, whatever we get from we had sampled, is used for updating the prior parameters, and we get the posterior parameters of the state, and we set the next state to be the posterior parameters, and the number of remaining trials will be t minus n1 minus n2. The phase will move from t to p plus 1, and the reward is computed by in the same way as I explained before, where the regret for the terminal phase would depend upon the action selected for the terminal phase. If we had selected, so if the actually here we can compute two things. One is the delta is nothing but the difference between the true means, and delta hat is nothing but the difference between the estimates of the true means. If the delta hat is in the same size, same sign of delta, that means that we have made the correct allocation for the last phase. So that is for the exploitation phase, and if not, then we have not made the right allocation. In such cases, a regret which a regret term will be added along with the regret for the previous phase. So using this algorithm, we actually get the Q table, and from the Q table we can find what is the optimal action for a particular state. So now going to the results and validations. So we tried using the algorithm with setting t to be 0, I mean t to be 50, and sigma m, sigma e to be, those are the parameters. We've just set it to 1 and 1 in this case. And we can see that. So we have tried to validate the Q-learning approach. In order to validate the Q-learning, the framework, whatever we have proposed, we have tried to compare the approaches with two different approaches. One is the theoretical approach, which was proposed in the paper Nandan et al., which I discussed before, where they solve the cumulative regret equation and then they get the optimal results. And another one is the simulation approach, which is nothing but the brute force one, which we all also discussed before, where all the actions are tried some number of times, and then the cumulative regret, the expectation is taken over the cumulative regret, and the minimum from that is selected. So of the three, we can see from the results of the three approaches that our Q-learning approach aligns well with the theoretical framework and the simulation approaches. So we tried this for a different environment where the noise is changed, noise in the environment, the system noise is changed from 1 to 3, and we find that our results work well with our framework, work well even with a changed environment. So, and it is like from these two graphs, it's obvious that with the increase in the noise in the system, the amount of resources which is required in the first phase, that's the exploration phase, is higher. So this is a validation for number of phases being 2, which was already there. So we are just checking how our RL setup works in this framework. Now we have to validate our experiments for the number of phases being more than 2. So say we take a 3-phase. We take a 3-phase problem for this case, and as I said before, in order to validate, we can't use a theoretical framework, as the theoretical framework is quite hard to extend it for more than 2 phases. So here we introduce a quasi-simulation approach, where in the first phase, actually all the actions are tried equally for some selected number of times. And in the second phase, so based on the first phase actions, we update the prior. Initially, we assume no knowledge about the prior, no prior knowledge, and then after the first phase, we update this the knowledge. So we update the distributions, and we have some knowledge about the experiments or the environment in which we are working. In some way, the posterior will be more aligned to one treatment than the other treatment, and such priors can be called as an unequal prior. And so an analytical solution for such unequal prior 2-phase formulation was proposed in Nandan et al. So we use this framework for the second phase to determine that the optimal action for the second phase. And so on the whole, we obtain the results using the quasi-simulation approach as well, and to see that our RL framework, whatever the results which we obtain from the Q-learning framework, aligns well with the results obtained from the quasi-simulation framework as well. So this could be a valid proof for the to say that our proposed algorithm works well for phases more than 2. So now a comparison of the resource allocation is made for problems with more number of phases. So this is the actual problem. Till now we were discussing about a 2-phase problem and a 3-phase problem, where the first and the second phase we can do the exploration, and the third phase was considered to be an exploitation phase. So here the comparisons are made keeping all the other parameters constant, like the T, the number of trials available, and the prior distribution, keeping all the other parameters constant. We are going to only vary the number of phases in which the experiments are conducted in. So this framework shows how for 3 sets of experiments. First is when we consider only it as a 2-phase problem, and then second is when we consider it as a 3-phase problem, and how it is approached when we consider it as a 4-phase problem. For the 2-phase problem, it's quite simple. Even the results can be obtained theoretically, as mentioned before. And so since we don't assume any prior knowledge about the experiments, equal allocation is made between the 2 treatments. And when you go to a 3-phase problem, what happens is that after the first phase, based on the results, whatever is obtained, we update the priors. And we get a posterior distribution. The interesting point to note there is that in the posterior distribution, the mean of the posterior distribution itself becomes a distribution, while the variance of the posterior distribution is a constant value. In this case, it is 0.16. And since the mean in itself is a distribution, we actually, in order to show some of the policies, we actually had taken 3 samples at the 45th, 55th, and 50th and 55th percentile of the distribution of the mean. And we can see that how the resource allocation varies. So if the mean is like minus 0.015, it is more aligned, the results from the first phase is more aligned towards the second alternative, whatever is chosen. And if the and when the mean is 0, which means that equal, again, it's similar to the first phase where equal allocations are made. And when the mean is positive, it means the first phase, because this is nothing but the distribution of the gap, right? So when the mean is positive, then the allocations are made in such a way it is more inclined towards the first treatment. So an interesting point to note from this thing is that while actually allocating resources phase-wise, the amount of resources which is allocated to each phase is primarily dependent on primarily and only dependent on the variance of the posterior distribution, which is received from the first phase, or the prior distribution for that phase. While the sharing of the resources between the 2 alternatives, that is primarily dependent on the mean of the posterior distribution, which can be clearly seen from this. So the same structure moving to a 4th phase, we have just shown the scenario where after the first phase, you update the distribution, and these are 3 samples which is taken from the distribution. And for the second phase, each of this is again, each of the distribution is again updated to get a posterior distribution, whose mean is also again a distribution, and some states from there is selected, and the resource allocation policy for all that is shown in this figure. So on the whole, this research, the main aim of this research is to provide the optimal resource allocation on each phase and to the practitioners. And once the practitioner chooses, once a practitioner chooses how many number of phases he wants to operate it in, so our research can be used for 2 main purposes. One is to find the optimal amount of resources to be allocated to each phase, and second thing is that what is the percentage of resource allocation that is made between the 2 alternatives, between all the alternatives. In this case, it is the 2 alternatives. So this can be extended. So our framework can be extended for T, which is greater than, for number of cases being 5, 6, 7, and so on. So in terms of future work, this idea, as I said, is actually derived considering there are only 2 treatments, and 2 treatments are alternative. It is fairly extendable to more than 2 treatments as well. And now we have actually used a tabular approach to approximate the Q value. Instead of doing that, when we go for more number of phases, there will be more number of scenarios or states which we need to accommodate also. So in such cases, if you use the state-of-art DL techniques to approximate the complex cumulative regret function, it would be much better. Thank you, sir.
Yeah, thank you, Ramya. And that was a very nice connection between experiment design and RL.
Yes, sir. Thanks.
I encourage people to post questions in the chat box. I mean, we'll take a short break, and in the meanwhile, if Ramya can post responses. But I can just have one couple of questions. You said it can be extended to, you shown results for 4 phases and so on, right? And you said it can be extended to a larger number of phases. So what is the downside? I guess some computational complexity, or what is what is the downside to that? What is the trade-off rather?
So yes, sir. So actually, as we go for more number of phases, like currently in our framework, what we are using is a discrete setup. So here, which means I've discretized the state space and I've discretized the action space. So, but when we, so it won't work well. So when we go for more phases, as I showed you in this thing, as I showed you, when 1 minute. So, in this framework, as I showed you, each distribution after each phase itself will end up in a distribution of distributions. So the number of scenarios which you have to evaluate becomes exhaustive. So that's the major downside, and this can be overcome or overruled by using the neural network techniques, where you can actually find the approximation. Here I have formed it. I have actually tried and used a tabular method to approximate it. So to find the Q values, but instead you can use the function approximation techniques to do that.
Okay. But I guess that will come with its own challenges of training the neural network.
Sorry, sir.
That will come with its own challenges of training the neural network. And so on.
Yes, sir. Yes, sir. Yes, sir.
There is a question by Govind. If you can open the Q&A box. So there's one question, maybe if you have time, you can answer it, and then we'll take a break.
Yes, sir, sure. Is there a possibility that the method have any limitations applying to experiments with more factors? Typically, practical experiments will have numerous factors. Is there a mechanism to prioritize on factors? So yeah, so currently we have not considered, like, we have only considered the alternatives as we have considered a very layman thing, where we have just considered a setting with two alternatives. We've not two levels, a setting with two levels. We've not one factor, two level setting. You can, if you put in the experimental framework language. So yeah, maybe this research can be extended to more than two factors in future. And if when extending, so maybe there can be mechanisms which can be used to prioritize these factors, but currently we have modeled only for an one factor, a two level setting.
Thanks. Is there a question from Arun?
Hi, Sridhar. Yes. Yeah. Hi, Ramya. Nice talk.
Yes, sir.
A general question about the setup itself. So two motivations that you gave for this method is, one is you may not get reward immediately. The other is there might be some kind of a problem with changing the
alternatives. Yeah, at each trial, picking the alternatives. Yes, sir.
Yeah. So people have studied both of these in the bandit setup itself, as, for example, multi-arm bandits with switching costs, where when you switch an arm, you actually pay 1 unit of cost for that. And also the case where bandits with delayed rewards. Should we think of this as some way of combining both? And are you aware of these words, and how do these ideas compare with that?
So yeah, so actually, when you take the banded approach for the experiments with delayed responses, still like after each trial, we have to wait until the response is received, though, sir. So, but in our case, maybe like I have to go through, sir. I have to go through what is that.
Sure. Yeah, so it might be good to look at those works as well and see how that relates to what you have done. Just a suggestion. Yeah. Thanks.
Sure, sir. Thank you, sir.
Thanks. And there's another question by Govind. Maybe you can respond to him on the chat box or the Q&A box. So we, in the interest of time, we will now stop, and thanks Ramya again for the very interesting and stimulating talk. We will originally planned a 10-minute break, but I'll have to cut it down to 5 minutes. You're already running late. So we'll reconvene at 11:15. The time as per my clock here is 11:09. So we have around 6 minutes break. We have 3 more speakers after the break. Meanwhile, during the break, we have a very short video on the center. Those are not familiar with the center. This is a very good opportunity to get some more information. So Ravi had put in some plugs about the different schemes in which you can work with us. This will also give you some other information about the different activities of the center. Thanks, and again, we'll reconvene at 5 minutes.
Hello everyone, I'm Ravindran, a faculty in Computer Science and Engineering at IIT Madras. I also head the Robert Bott Center for Data Science and AI at IITM, one of the largest interdisciplinary AI centers in India. So the center started operations back in 2014 as an interdisciplinary lab for data science, wherein faculty from 6 different departments got together to start this group. And we started off small scale with 3 projects. And today, so we are the Robert Bott Center for Data Science and AI. We started operating in this avatar in 2017. And now we have 28 faculty members, more than double our size, across 10 departments in the institute. And so we have more than 120 plus publications in the past few years, and as well as run 23 different interdisciplinary projects. The various areas that in the fundamental research areas that the center looks at, right? So we are having a significant focus on looking at data science and AI applications in various engineering disciplines. And network data is something that arises often both in engineering disciplines and across other areas such as biology, transportation, social media, telecom, and reaction networks. So the idea here is that you're not looking at entities in isolation, but looking at interactions between entities as well. And so we have, our center has one of the largest groups in the country that looks at network data across different disciplines and also take advantage of the synergies that arise. So we also have a very large group that looks at deep reinforcement learning. And so we have certainly published extensively in the last few years, and we are the largest group in India in deep reinforcement learning. And we also do a significant amount of work in explainable AI. So we have people who work on explainable visual classification and looking at explainable power of attention in language processing and looking at the dynamics of learning in deep networks. Also learning on interpretable small models and interpretability in healthcare and other specific applications in manufacturing domain and so on. So the other areas that we work on are looking at social impact of AI, causality, both from a process modeling point of view as well as more classical AI notions of causality, and robust learning, learning with guarantees and learning with limited and partial data, which often arise in engineering disciplines, and also human in the loop learning, where the human is either an expert or could be just an operator who is trying to interact with the AI system. So as you can see that many of the themes of fundamental research arise from looking at specific application verticals. So we have groups that work on manufacturing analytics, financial analytics in collaboration with the DART Center, and also systems biology and healthcare. That's a good fraction of the work that happens at the center is on systems biology and healthcare, and that's in collaboration with IBSC, another center here. And we also do a lot of work in smart cities. We started with looking at traffic. Right, traffic engineering, and now we look at general smart mobility, water distribution, power grids, and also construction, pollution, various aspects to do with smart cities. And so we just not do these kind of fundamental research work. At this point, we are starting to make an impact at the global level as well. So some of our recent work, for example, GrabQC, which is query contextualization for automated coding in a medical domain, won the Best Application Paper Award at PAKD 2021 recently. And before that, we had a paper on explaining deep convolutional nets for image classification that won award at WACV 2020, one of the top vision conferences, as the Best Paper Award. And also at COTS-COMED, a conference organized by IKDD. So we had a paper that won the Best Paper Award for work on class and balanced learning, and then this continues. So in AMAS 2020 last year, we had a top 4 recognition for a paper that used reinforcement learning for discovering structure of social networks, unknown social networks. And then we had a best applied paper runner-up in COTS-COMED on our work with for-hire vehicles. And more recently, one of my colleagues worked with collaborators in Stanford was accepted at Nature Communications on looking at applying network science and control theory to understand dynamic brain circuits. So apart from these kind of research impact, the work at the center is also have significant societal impact. So we collaborate with multiple governmental bodies as well as NGOs in looking at several socially relevant projects. For example, we helped the Tamil Nadu government set up the CM helpline, and also we work with closely on the COVID war room currently. Right? And you can learn more about our socially relevant work at our blog. Right? So continuing with our focus on social relevance, we also launched a fellowship on AI for social good for early career researchers. That's funded by the Narayanan Family Foundation. And so it's a very attractive benefits. Please look up the advertisements online. Right. So we have also contributed significantly in terms of number of tools and data sets that we have released. Samanantar is a large Indian, the largest Indian language corpus that has a parallel corpus that has been released. So far, it's done primarily by the AI for Bharat organization, but supported by the Robert Bosch Center. And we also have other data sets such as the Indian traffic data set of HETRA. It's a small data set, but carefully labeled, and also multiple data sets across the different biological problems that we have studied. And RBCDSAI, apart from getting involved in fundamental research, we have also launched several first of its kind programs. Right? So the first one, at least in academia, this is the first such program, the Post-Baccalaureate Fellowship, wherein we give a 2-year research fellowship for exceptional graduates and postgraduates. And this is modeled after some of the programs that the top-notch research labs in the country have. And we have had significant success. We have had about 14 post-baccalaureate fellows so far, and many of them have produced excellent work, excellent research that resulted in top-notch publications. And some of them have turned around and joined us, and some have gone on to do PhDs abroad. And we also have this interdisciplinary dual degree program in data science. We are the first IIT to launch a degree program in data science, and where the graduates get both the BTech in engineering discipline as well as an MTech in data science. And the focus is on training them in applying the data science ideas to their parent discipline. And we also have this 11-month certificate program in collaboration with IIM Bangalore, which straddles both technology and management. And we have launched the industrial consortium model, wherein we get partners, industry partners who work closely with RBCDSAI and partner with in various events that we run at the center, right? So that they can get more exposure to the kind of research that happens here, and also this leads to better dialogue. And we have had excellent feedback and enthusiasm from the consortium partners so far. And we also have launched an associate researcher program, wherein we allow people or we invite people from the industry labs as well as from other institutes like some of the newer IITs to associate themselves with the center, and so they get to co-advise students, we get to co-write project proposals, as well as take part in some of our workshops and other programs that we run. Right, and this is a fellowship spread over 2 years, and we have had multiple very interesting outputs come out of this already. So here are some numbers. So like I mentioned in the beginning, so we have about 28 faculty spread across 10 departments who are part of the center. And we have about 80 plus researchers, 6 of them who are postdocs, and about 10 post-baccalaureate fellows are there currently, and about 50 plus research scholars, both at PhD and master's level. And as I mentioned earlier, we have 120 plus papers that have come out, of which more than 50 have high impact conferences like A-star rank conferences and very high impact factor journals. And we have collaborations across the board. This is like just the mind-boggling number of collaborations that we have both in the industry and NGOs. And we can also see our international collaboration footprint is fairly large going now. And hopefully we are looking to expand this much further as we go down the years. Right. So one of the new research initiatives that we have launched this year is looking at what we call as deployable AI. So doing AI research in the laboratory is fine, but when you actually try to deploy it in the field, a lot of things that could go wrong. So we are looking at it, multiple facets of this, looking at fairness and social relevance of AI, explainability, transfer learning, right, and also privacy and safety in AI, and also AI on the edge. Right, so this is when or like federated learning. So where you want to make sure that your distributed AI systems work great well in synchrony. Right, so there are multiple projects that we already launched in this theme. Right, so we are looking at AI and ethics in the Indian context, especially looking at notions of fairness in Indian context, and also looking at how deployment of AI could further marginalize populations which are already suffering due to the digital divide in India, right? And then we're looking at various interpretable models and algorithms for human in the loop learning. And so this is essentially where the human should understand what the AI is doing before they can react to it. And then we have fairly a couple of projects that are running on interpretable deep learning, especially in the context of healthcare, and also looking at incorporating domain knowledge in an interpretable or explainable manner into machine learning models, so that domain experts are having a slightly increased comfort level when they are looking at the prescriptions of the machine learning approaches. Right? So there are multiple ways in which you could work with us. Right? So we have the postbaccalaureate fellowship, as I mentioned earlier. We also do multiple internship program, including a global summer internship program, and the fellowship, that's a postdoctoral fellowship, as well as the RN family fellowship. And we also have a new certificate program that we launched with Talent Sprint. So please look that up. And RBCDSAI is on social media and is on the web. And please look up our YouTube channel, our Twitter channel, and everything for more information about us. So do write to us if you're interested in joining us or interested in knowing more about the center. You're always welcome that. Thank you.
Thanks, and yeah, we are running around 10 minutes late. Sorry about that, but I am guessing as long as we learn something, it's useful. So the next speaker is Saarthak, Marathe. Saarthak is a final year dual degree student pursuing BTech in mechanical engineering and interdisciplinary MTech in data science. Previously, he's been part of, he spent time in the ISIR Sorbonne lab, Sorbonne University, doing a research internship in robotics. He was also involved with the Adobe Big Data Experience Lab as a data research intern. He's currently working with Professor Neerav Bhatt and Professor Ravi in the field of SAFE RL, looking into possible human intervention and applications. Over to you, Saarthak. And
yeah. Thank you for the introduction, sir. I'll just share my screen.
Yes, please share your screen and.
Do let me know if my screen is visible.
Yes, it's. I can see the full screen. I'm sure others can also. Yeah, please carry on.
Yeah, all right. So, hello everyone. As Professor Sridhar said, my name is Saarthak. I'm in my final year dual degree of mechanical engineering and interdisciplinary data sciences. And my project, like the dual degree project, under the guidance of Professor Neerav Bhatt and Professor Ravindran, is in the field of safe human in the loop reinforcement learning. So before getting into what human intervention that we are looking into, let's understand what is safe reinforcement learning firstly. So the aim of safe reinforcement learning is to create a learning algorithm that is safe while testing as well as during training aspects. So to give examples, one of the examples could be when data center cooling, for data center coolings, temperatures and pressures are to be kept below respective thresholds at all the time. And when for that to happen, reinforcement learning agent training needs to be safe in nature. Other could be like when a robot is being trained in a constant environment, it should not exist a particular velocity limit or angle limit or torque limit while it's being trained. And the third could be when an autonomous vehicle is running on the streets, it must respect its kinematic constraints, like it should not run over someone or it should not go on the footpath or so on. So to define what safe reinforcement learning is, it's a process of learning policies that maximize the expectation of the return in problems in which it is important to ensure that the reasonable system performance is given and the respect of safety concerns during the learning and the deployment processes. So to approach these issues or this particular sector, there are two major ways of doing it. One is to change the optimization criteria for the learning, and the second could be change in the exploration processes. Now, going over the change in the optimization criteria aspect, it could be done in three major ways. based on the literature in this particular field. First is the worst case criteria, second is the risk sensitive criteria, and third is constraint criteria. So looking into the worst case criteria, policy is considered to be optimal if it has the maximum worst case written and the policy's worst case reward obtained is maximized. So for example, as you can see in the figure below, the red one is which signifies this particular worst case criteria. And an example for it could be like the gambler is playing in a casino, will use this particular red graph. The reason is that it gives a more expected reward. But whereas if you really look into an agent, if it's a surgeon, it will follow the blue graph because the blue policy works better because it has lesser variance, and that is why the less chance it will screw up because low rewards are less probable. This is where the risk sensitive criteria comes in. So the idea over here is to include the notion of risk in the long-term reward maximization objective. And in some of the literatures, it defined risk as the variation of return. And the methods of doing it is maximizing value at return and conditional value at return. I wouldn't go completely into detail, but the gist is basically based on the blue graph. Now coming to the third criteria is the constraint criteria. The expectation of the return is subject to one or more constraints. So for example, a policy is updated if it is safe with a certain confidence given the constraints. That is what it intuitively means. Now going over the change of the exploration processes, it could be done in two major ways. One is to incorporate external knowledge and second is risk-directed exploration. So when we say incorporation of external knowledge, it basically is to provide initial knowledge, which could be a type of initialization procedure for your environment or the system, or derive a policy using a finite set of examples. So then an example for this could be that if we record a finite set of demonstration from a human teacher and provide it to a regression algorithm. And to build a particular Q function while can be used to guide further exploration. To derive a policy from a finite set of demonstration, teacher demonstrates a task and the state action trajectories are recorded. And all these trajectories are then used to derive a model of the system's dynamics, and an RL algorithm finds the optimal policy in this particular model. Now moving on to the risk-directed exploration. So one of the major approaches in this particular criteria is defines a risk metric on the notion of controllability. So for example, if a particular state action pair yields a lot of variability in the temporal difference error signal, it is less controllable. So the exploration algorithm seeks to use controllability as an exploration heuristic instead of general Boltzmann exploration, which is used for typical RL agents. And the agent is encouraged to pick controllable regions of the environment. So another major aspect over here are the constraints. The first, they're divided into two major parts. One are the hard constraints and the second are soft constraints. So the hard constraints are followed. When we say a particular constraint is hard, we mean that it's followed without fail while training and testing. And whereas a soft constraint could be which are not necessarily followed while exploration, or sometimes they are followed in expectation. So an example could be like a constraint quality optimization or a safe multi-agent reinforcement learning for autonomous driving. These are the major two literature which cover soft constraints aspect, and hard constraints could be like safe exploration in continuous action spaces and or trial without error paper, which looks into safe reinforcement learning via human intervention. So now, as we have covered like why what is safe reinforcement learning, now we'll look into what is the motivation of involving humans while doing safe reinforcement learning. One of the major, there are three major aspects to it. First is the artificial intelligence scalability issue. So as AI has broadened over time, the real life application in different domains have increased. And the major apprehension regarding these are in the fairness, safety, security, privacy, and failure of ML agents. And secondly, the apprehensions from usage in safety critical system has increased because the learning algorithms are rarely used in the real world safety critical system because of the issues with handling critical human situations. And thirdly, extremely effective technique for inferring optimal policies from experimental data and the discovery of the optimal policy, which may be detrimental to real world system. So essentially, to solve these issues that exist, we model human participation as a specific consent provider in the work to ensure safety while exploration. And we handle trade-off between short-term actions and policy optimization in the work that we have done so far. So to define the problem statement, it's regarding human involvement in exploration of safe spaces. We propose an algorithm for achieving human intervention in maximizing the optimality of cumulative reward while guaranteeing safety in a constrained markup decision processes environment. So for this, we take a MDP, which has S as a finite state space, A, which is a finite action space, F is a deterministic transition function, R is a reward function which uses GP as GP prior, and G is a safety function which uses again a GP prior, and gamma is a discount factor. Over here, to note is that the reward function and safety functions are not known a priori, and they're modeled using the GP prior. We denote a value function VM in the MDP, and then the problem statement is to maximize the value function for the policy and the MDP M, and it's subject to G, which is the safety function, and H is the threshold value for the safety function, and essentially a hard constraint. Now, to look into what actually the algorithm is. So the algorithm requires the state action, the other functions, the kernel for reward, the kernel for safety, the GP priors for safety and reward, the H, which is a threshold, gamma discount factor, Lipschitz constant is used, initial safe spaces are required, and human intervention systems. So the algorithm is majorly divided into three parts. First is incorporation of human intervention. Second is exploration of safety. Then is exploration and exploitation of reward. So for incorporation of human intervention, the RL agents action, policy, and reward are modified to become A star, pi star, and R star. And during the exploration of safety, we define a pessimistic and optimistic region of exploration. And we make sure that there is returnability and reachability of states being followed. And then finally, we use conventional methods to terminate these conditions based on conditional probability. And lastly, after doing this, we update the probabilistic limits of the upper limit of the bound, and we check the Bellman equation for the terminal point and update the state spaces explored. We'll go through each one of these stages one by one. Now, firstly, looking into incorporating human intervention. So we over here at the safety exploration stage, we take a system which is defined by pi of human and P, whereas pi of human is human a priori known policy, and P of S is possibility of intervening at S state. And these systems in combination with the action, policy, and reward of the RL agent would be modified to give A star, which is PT into A of human plus 1 minus P into A. PT is basically takes a value between either 0 or 1, and it's a Bernoulli of P of S. Then policy similarly in a similar fashion gets upgraded to pi star, which is P of S into pi of human plus 1 minus P into pi of agent. And R star reward has a new addition of hyperparameter delta into P of T, which again takes value of either 0 or 1. And this hyperparameter delta is one which is used for the scoring of the system. And these hyperparameters for each state spaces at a particular time t would be used for the testing bed as well. Now, looking into the exploration of safety, as we mentioned before, we firstly define the pessimistic safe spaces and optimistic safe spaces. So defining what they exactly are, a pessimistic safe space is the contained state identified as safe with a greater probability than a predefined confidence interval. An optimistic safe space includes all the states that may be safe with even a small probability. Now looking into the reachability and returnability aspects of the state spaces. So according to Tusheta et al. 2016, it defines reachability as a property of states that can be reached starting from a safe set in certain number of states. And similarly, returnability is basically a property of state where we are able to return to a previously visited safe states through some other set of states. So just to put in simple terms, reachability is basically from one state space, you should be able, safe state space, you should be able to go to the other one. And returnability is like, let's say if you are at say a safe space ST+1, you should be able to return to ST and ST-1 and so on and so forth, the previous safe spaces. The reason of doing this is because it basically defines a safe region, and it also says, and also tells us where the termination criteria of safe spaces should be. Then lastly, for the termination condition of the exploration, efficiency of expanding the safe region is measured by the width of the safety functions confidence interval, so which is defined as WS, which is U add S minus L of S. And conventionally, the termination is the termination equation which is used is max of W of S should be less than equal to epsilon of at G. So now looking into the third stage, which is exploration and exploitation of reward. At this point, all the agent has to do is to optimize the cumulative reward in a certified safe region, and it leverages algorithms for optimizing unconstrained MDPs. So a simple approach is to follow the optimism in the face of uncertainty principle. And for balancing the exploration and exploitation in terms of reward, we solve the following Bellman equation where J is equal to max of UT of ST+1 plus gamma J of ST+1. Basically, the UT is the probabilistic upper confidence bound of reward, and the ST+1, the criteria is the next state must be in pessimistically identified safe spaces. Now looking into the simulations and the results we have gotten so far. So we use a synthetic GP safety gym on OpenAI. Basically, at each step, an agent selected one of the actions where it could stay, it could go up, right, down, or left. And on the basis of previous observation, the agent anticipated the reward and safety functions using the several kernels which were defined. So what we did is this particular algorithm is called safe near optimal MDP algorithm, and we compared it with the other previously known algorithms in a similar spaces, which is like the safe MDP, safe exploration optimal MDP, and safe reward unknown, safe reward known factors. What we found as results were that in safe MDP, the agent attempts to increase the size of the safe region regardless of the incentive. But this safe exploration optimum MDP aims to maximize the cumulative reward by utilizing the difference between the value function in the optimistic and pessimistic safe spaces. And safe reward known is basically a non-experimental scenario in which the safety and reward functions are predefined. That is used as like a base for a comparison. And for the comparison matrix, we use cumulative reward and the number of unsafe actions. And the results we saw was the average reward was measured over the previous 50 time steps. And SNO MDP, which is a safe near optimal MDP, achieved the optimum reward after shifting to a stage of reward optimization, which outperformed the previously known safe MDP and safe exploration optimum MDP in terms of the reward after a sufficient large number of time steps. Yeah, this is all I have for right now. And in terms of future work that we are doing is we have emulated this model in a Mars OpenAI gym, and currently working on implementation of the algorithm that was proposed in the slides previously in into coding format, and also looking into other ways where the human intervention happens without knowing the policy a priori, only by knowing the action states and how it would modify the RL agent's actions, and look into the scoring, and the scoring could be used for testing. So yeah, that's all from my end. Thanks a lot.
Thanks, Saarthak, for the interesting talk. If there are any questions for Saarthak, please use the Q&A box. Not, I have, since you talked about constraints, are there some similarities between this and model predictive control, if you're familiar with MPC?
So unfortunately, I'm not completely familiar with MPCs.
Then since there is also constraints, right? Do you do any truncated distributions because and so on?
Between the constraints,
Yeah, so let's say, I mean, I'm just asking the first figure that you showed, right? I mean, now there are, do you work with truncated distributions to ensure that, you know, your whatever you get is within a distribution? I'm talking about things which naturally take values in only a certain range, not about the constraints on your action.
Yeah. So yes, so we try to model it as a continuous distribution, because that would
no, that's suppose there are no. What I'm saying, suppose there are output variables which naturally will fall only within constraints. For instance, mass fractions or normalized numbers and so on. So rather than use a continuous distribution from minus and continuous normal distribution, do you work with constrained distributions where the support is, it has only a finite support. The distribution is only finite support. It is zero outside that support.
Yes, so that's where the human intervention part came in. Where I mean, yes, you're talking from the constraints perspective, but yes, we use finite distributions as well for the constraints aspect.
Okay, thanks. If there are any other questions, you know, I will ask Saarthak to keep an eye out on the Q&A box, which you can respond to in leisure.
So I think someone has raised their hand. Maybe if they could write in the Q&A box.
So let me see who has raised the hand. Yeah. Oh, yeah. Let me. So yeah, they could possibly raise, type the question in the Q&A box, because I'm not sure who it is who has raised the hand.
I could answer the. I think we can go on with the session, and I could answer.
Yeah. So I'm not able to find out who has raised the hand. I encourage them to type the question in the Q&A box or the chat box, and Saarthak will keep an eye out for the question and respond to it or the Q&A box. And let's thank Saarthak again, and we will go to the next speaker, who is Nishant Prabhu. Nishant is a final year of his BTech in Mechanical Engineering and MTech in Data Science at IIT Madras. He is working under the guidance of Professor Ravindran. His primary area of interest is deep learning for computer vision, in which he likes to work on self-supervised representation, learning, and model explainability. He has one accepted journal publication in ReScience 2021 as part of New IPS ML Reproducibility Challenge. In his spare time, he likes to read books about spirituality and the subconscious. So today he is going to be talking on explainable reinforcement learning. And over to you, Nishant. And
yeah. Thanks.
It takes around 15 minutes to 15 to 17 minutes to the talk.
All right, sir. Yeah. Thank you for the introduction. I'll bring up my screen so that.
Please share your screen. Yeah.
Please let me know once you can see it.
Yeah.
Just a second.
Yeah.
It's visible. It's visible.
Yeah, go to full screen.
Trying to. The zoom bar is hiding the slideshow button. Yeah. Okay. Okay. Good morning, everyone. As mentioned, I'm Nishant, and I'm being guided by Prof. Ravindran from RBCDSAI. And today I'm here to talk about explainable deep reinforcement learning. So in the previous talks, we saw a lot of applications of reinforcement learning, right? In different areas. For example, we had autonomous driving related applications in the previous talk. And Professor Ravindran in his talk mentioned something about humanoid robots being able to play soccer trained with RL. And we've also had algorithms that have made it big into the news, right? Like AlphaZero, which has been able to outperform even the best computer non-RL based algorithms in games like chess or Go or Shogi and so on. So the point is, we've had very impressive performance by RL in many tasks. Like this is a slightly constrained list. We also have applications in the healthcare industry, suggesting therapeutic procedures based on the diagnostic of patients, or in the financial industry where you might want to execute financial transactions in the stock market and so on. But the problem is there have also been cases where AI, if not monitored carefully, has led to loss of either dignity or property or sometimes even life of the stakeholders because it behaved in an unexpected manner, possibly because it had not experienced a particular situation in the past and it did not know what was the best way to handle it. Right? So since these problems exist and we would like to trust the AI that we deploy in the real world, it makes it imperative to develop some methods wherein if an AI is deployed, we would like to know what it is thinking when it is making a certain decision. And this particular study falls under the area of what we know as model explainability. So this is what my talk is about. And in the next 10 or 15 minutes, what I would like to do is go over some of the methods which talk about explaining deep reinforcement learning, which basically pertains to RL, but using deep neural networks as the agent architecture. And some of the existing work that exists in it, we'll talk about that. And also some of my work, which I've been doing with Prof. Ravindran. And we'll see how the results have been. Right? So now that I've motivated that explainability is needed, let's see what we can get out of deep reinforcement learning. If we explain, right? This is the image that you see on the slide is the standard reinforcement learning setup. You have an agent which executes some actions into an environment. The environment undergoes some changes, which it provides back to the agent in the information about the state. And apart from that, it also gives a reward to the agent, which kind of evaluates how good the action that the agent took was. Right? And in the scope of deep RL, this agent, more often than not, will be modeled as a deep neural network, like possibly with several layers. But the problem is, although this deep neural network is very versatile and it can do a lot of things, the deeper you make it, the more less explainable it becomes. So it's like a black box model, right? So neural networks versatile but black box. And from the fact that these neural networks are a black box, we have trouble answering certain questions. For example, how will it behave in unseen situations? Assume you're sitting in a vehicle which is autonomously driven by an RL agent. If it encounters a traffic situation or a road condition that it has not been trained on, how will it behave? It's a question of your life. You would really be interested in knowing what happens there, right? And also things like, is it possible to have a simpler model? Because the simpler model we can have, the better we are, right? Because it's very easy to explain simpler models, and that is what we would like in the end. So this is why explaining DRL in particular is needed. Right? Now, then the next natural question to ask is, what is it in DRL that we can explain? So if you can see the figure on the diagram, this is a standard setup in the case of visual deep reinforcement learning, right? And when I say visual DRL, what I mean is agents that work on pixel-based visual inputs, like images, as you see on the left, this gray rectangle cuboid, which you can see on the left. And the agent could be something like a deep convolutional network, which is very popularly used for image processing applications. And what this agent will do is convert this image into, let's say, a feature vector, which will be like a low dimensional vector in a certain latent space, right? And then what happens is a Q network, which is usually a linear function, like a linear regressor, it takes in the features that were extracted from the image and learns what is known as a value function, which represented as Q. If you're not familiar with what a value function is, basically it tells you in a particular state S, if I take action A, what is the reward that I can expect at the end of the trajectory? Right? So it basically tells you how good it is to take a particular action given a state. This is known as a Q function or a Q value function. And then what will happen is there will be a policy which will take in the Q value functions, the Q values that are predicted for that state and action, and it will tell you finally what action is going to be taken in that particular state, right? So you can see that there are many different components in this pipeline, and it might be obvious to you that the methods for explaining each of these components will be different, right? Because the way they are built and what they do is very different. And what we would like to explain is possibly the features that are extracted by the convolutional network, or maybe someone would want to explain the value function, or maybe you want to explain the policy or the actions that are taken in a particular state itself. Like what would happen if that action was taken instead of this, and so on and so forth. So there exists several work which tries to explain one or more of these parts of the network, and I'd like to quickly go over those. But before I jump into the methods themselves, I'd like to categorize them into 3 different categories based on overall the method that they use in order to explain it. The first category is what I like to call distilling the agent's knowledge into an interpretable model. And what we do in this case is we use a trained DRL agent and we transfer its knowledge into a simpler model, like a linear regressor or a decision tree. And then we use the simpler model in order to, kind of explain the action that was taken by the complicated neural network agent. The second class of methods, which was known as the visualization of the latent manifold, and we look for patterns there, is where you do something like explaining the features that were extracted by the convolutional network. You take the features, you project it into a lower dimension like 2 or 3, and you visualize it in those dimensions, and you see if, let's say, there's a cluster of states where similar actions are taken, and are those states close by together in the latent space that the agent has got, something of that sort. And the third class of method that exists is known as post hoc methods, where what we do is we extract specific information from the trained agent and we visualize it and see if we can, figure out what the agent was looking at. For example, this image on the bottom, it's known as a method called class activation mapping. And what it points out is that when looking at this image, and if it classified as a bird, it was essentially looking at this region of the image when it made its decision. We can extend this similarly to RL. I've given an example of classification. So some of the methods that already exist, I'll quickly go over this. One of the methods is known as linear model U trees, where what they do is they train an agent and they distill its knowledge into a decision tree. So by distillation, what I mean is when it observes an observation or when it observes a state and it takes a particular action, you train the decision tree such that it predicts the exact same action given that particular state. So in some way, the agent is like a teacher and the decision tree is like a student. And when the tree has converged, what you can do is for any given state, you can traverse the tree, right? And you can see what splits it has learned for each of them. And you can convert this into a sequence of if-then statements. And what they do in the end is any data point that lands into a leaf node, they learn a linear regressive there, which predicts the Q values finally, right? So it basically distills the knowledge into a more interpretable model. Right, and another kind of method that existed in this was known as deep symbolic reinforcement learning, where what they do is they extract different kinds of features, right? So they give an image to a convolutional network and they get some features out of it. And then they try to bin those features into certain presets. And then they also extract something like spatiotemporal representations, how the objects are oriented with respect to each other through space and time and so on. Then the second kind of method, which tries to learn better representations of the states in a low dimensional space. There exists one paper known as learning invariant representations for RL without reconstruction. And what they do is they use what is known as a bisimulation method. So what the basic premise of this method is that states which are behaviorally similar should have similar representations in the latent space. And they should also result in similar rewards and the subsequent distribution of similar distribution of subsequent states when the same action is taken in both of them. So they devise a loss function, which basically enforces that. And then when they visualize the latent space, what you notice here is they have trained their agent on a driving simulation environment. And if you see the three images on the top, you'll see that they are very different situations semantically. Here you have a wall, here you have a car, you have a truck. But you can also notice that the overall action that the agent might want to take here is that steering to the left, right? Because there's an obstruction on the right, although the obstruction is very different in the three cases. And what you notice from this method is that all of these situations end up very close together in the latent space, right, after the steering. So that offers some form of interpretability to us. Another work that exists in this field is known as visualizing and understanding Atari agents. That went ahead. Yeah. Where what they do in this method is they ablate different parts of the state space. By ablation, I mean they perturb it or they occlude it. And they find out what are the regions which cause the largest drop in the value function when they are occluded. And what you can make out of that is, well, if I hide this region of the state, then it's causing difficulty for the agent to predict correctly, which means that region of the image must be really important for it. Right? This is how they highlight different regions in the image based on how important the agent feels it is. There was another work that talks about causal explanations of the agent, where what they do is they define some handcrafted situations. This was, by the way, an agent which was trained to play the game of StarCraft. And what they do is, given a particular state, they ask the agent, well, in this state, if you take action AS, what is the trajectory that you're expecting to see after that? So it has to go through a graph, and then it has to tell, well, from W, it will go to S, then S, I'll take AM, it will go to AN, and so on. And this is the reward I'll get out of it. Then you can ask, well, instead of AS, if you took AB, what would happen? Then it will give you another traversal through the graph, and it will tell you what reward you get, and so on. So that is another kind of explanation. So this brings me to the end of the literature survey. Now, what I would like to do in the next few minutes is talk about the work that I have been doing under the guidance of Dr. Ravindran, which is known as explaining DRL agents using self-attention networks. And what we do in this method is we have a trained agent that you can see here. It's a pixel encoder with a Q network. And if you give it certain observation frames, possibly from a game, so we train this agent on playing Atari games, right? So you give it a bunch of frames from the game, And it can predict an optimal queue function, and it can also predict an optimal distribution over the actions that are valid for that state. Right? So this Q star and pi star, that basically represents the action that is predicted by this encoder, and we treat that as the optimal action. What we do now is we take the very same observations, and from the output of the first convolutional layer in the encoder, we pass it through what is known as a self-attention network, whose architecture in particular we follow of the vision transformer, which is a fundamental paper published by a team at Google. So what a vision transformer does is it basically attends to several. So what we do is we break down the image into several patches, and that patch and the sequence of patches is provided as input to the vision transformer, and it basically learns, at what for this particular patch, how important are the other patches, how important is it to attend to the other patches, and so on and so forth. Right. And then at the end of this, I will not go into the details of this network, but what happens at the end of this is it predicts its own Q values and also predicts its own action. And what we do is we do something similar to the first method you saw in interpretable RL. That is, we again train this network to mimic the trained agent that we have using a cross entropy loss between the actual action and the predicted action. And what we do for getting explanations is at the end of, and is when this vision transformer is converged, we visualize the attention probabilities of the uppermost layer, right, which I will show you in the next slide. And that gives us some form of explanation about what the, the actual agent was looking at. So what are the benefits of this method? The first biggest benefit of this method does not depend on the agent architecture or the training method. As long as you have an agent that can predict any sort of action, we can use this method without making any change. Right? It is environment agnostic. Unlike some of the methods you have seen in the past, we do not have to handcraft any features or handcraft situations so that the agent can traverse through it and tell you what the explanation is. And that summarizes the third point as well. Right? So let's have a look at some of the results. Here you see some stills from some of the games inside the Atari benchmark suite. You have Breakout here, you have Space Invaders, you have Qbert, you have Pong. And the blue frames that you see here is basically the bright spots you see here are the high areas of attention that the agent had predicted. For example, for the Breakout, you can see that there is a lot of attention around where the paddle is and also where the ball is, right? For Space Invaders, you can see that there is bright attention spot near where the player's ship is. And there's also a bright spot around an enemy ship. And if you notice that, if you notice the video where this was taken from, you'll see that this is the ship that gets destroyed from the fire that the agent ship had just made, right? So it even attends to that. Now, in the case of Qbert, it is basically attending to some of the regions that the agent is going to visit next, right? So it also focuses on where the agent is and some of the regions that the agent is going to visit next and so on. That is some simple form of explanation. Here's a video that shows, the agent playing the game on the left. So you can see the screens that the agent notices while it is playing the game. And on the right side, you can see a live feed of the areas which the self-attention network predicted high attention at, right? So you can have a look at this entire video. I mean, when I make it open. But what I would like to show from this video is 3 particular instances where we made an interesting observation. So we saw that in the first frame, there is a situation where the ball is moving towards the brick after it has hit a paddle. And in the second frame, what's happening is it hits the brick and it begins to come down. And in the third frame, it is coming down again. So what happens is when it is moving towards the brick away from the paddle, the agent is only focusing on the ball's location. You see bright spots roughly where the ball is. But something interesting happens when it hits the brick and is trying to come down, right? You see that suddenly at this location, it is showing high attention around the paddle's location in the bottom row, if you see in the first and third hit. And then again, after it starts coming down after hitting the brick, you see that there is occasional attention on the paddle, but again, more or less, it starts focusing on the ball. So what you can make out of this is that when the ball is moving away from the paddle, the agent is not at risk of losing a life, right? So it does not really care about where the paddle is. It can just see where the ball is because you need to know when it starts coming down. But when it hits a brick and starts coming down, now the agent realizes that some action needs to be taken so it can intercept the ball and avoid losing a life. So it starts attending to the paddle in the second frame. But again, after it comes down sufficiently, you can see that sometimes it looks at the paddle, but again, more or less, it is focusing on the ball because it has taken the action that it needs to take to intercept the ball. So that is one interesting observation. There's another thing that we did, which basically visualizes the latent space that was learned by the attention network. And we do k-means clustering into 4 clusters in this particular example. And if I play this video, you will notice that you can
Media such as biology, transportation, social media, telecom, and
right. You will notice that this video basically shows the agent moving through different clusters at different points of time based on the state that it is observing in the middle frame, right? So you can see basically you can reduce this latent space into like a set of clusters which can be visualized as an MDP or Ensemble. And on the right frame, you can see the red line basically depicts the value function that was predicted by the agent. And the blue line, which is masked behind the red line because the predictions are quite good, is the actual discounted return that the environment received, then the environment gave the agent when it was played from that particular state, right? So this is another form of interpretability which caters to the second class of methods, that is visualizing the latent spaces. So that kind of brings me to the end of my presentation. I would like to summarize the takeaways. That is, one, explaining AI, which is for deep RL in our case, is quite important for us because for whenever an AI is deployed, we need to trust it to be able to use it in a carefree manner, right? And lots of methods exist to explain DRL agents. We looked at 3 kinds of methods. I also discussed my work and so on. And my work was pertaining to self-attention networks, which can also be used to generate explanations. And there's one point that I'd like to mention before I close is that trust is subject to personal biases. So is the issue of explainability. So what that means is, what that implies for us is, whenever we develop a method to explain an AI agent, it should be made as general as possible so that it caters to the apprehensions of as many stakeholders as possible at the same time, instead of making it limited to a certain set of environments or a certain set of experiments. So that's actually the end of my presentation. Thanks a lot for being such a wonderful audience. And I'll probably go over to the question answers now so that I can answer any questions that I have. I'm going to stop sharing my screen.
Thanks, Nishant, for getting us back on time. We have time for quick questions. The audience members can either use the Q&A box or the chat box. Okay, Nishant, I have one question. Over the last slide, you talked about use the 2 words interpretable and explainable. Are these interchangeably used, or do they refer to 2 different things? I see people intuitively, it looks like they're
Yeah, they actually are 2 different domains, right? So if I have to clarify that, what I understand out of interpretability is that there exists a system which can inherently be explained. You need not, you do not have to explore it separately or use a different method in order to understand what it is doing. For example, if you train a linear regressor on certain data, what you can do is you can simply look at the weights that it has learned for different features in your data, and that can sort of act as an explanation of the model on its own. So you don't have to really do anything extra on the model in order to explain it. So that I would call an interpretable model. A decision tree would be another example. Right? But explainability is a different game altogether, and that is like an umbrella topic. So explanation can be done for any model, whether it is simple or difficult, but it makes sense for difficult models because they are not interpretable, unlike the examples I gave earlier, because they are very complex. For deep neural networks, you have several different layers which act as nonlinear transformations, and the function becomes very complicated. So you cannot interpret them, which is why we need different methods which fall under the domain of explainability, right? So that we can use a different kind of model or a different method in order to be able to interpret this difficult system. So that's what I understand from the 2 terms, and certainly they're not interchangeable, although in common conversation they probably are used that way. But yeah, I hope that clarifies.
Thanks, Nishant. And Anish has raised a couple of questions in the Q&A box. Do you want me to read?
Yeah, I can go through them. I'll look. So, would you want me to take them live, or should I answer them?
Yeah, we have time. We have a minute, so you can answer it live. Yeah.
All right. Okay. So Anish has 2 questions. The first question he asks is, human in loop RL some way of providing explainability? That's a good question that somewhat connects what Saarthak was talking about and what I was talking about. Human in the loop RL somewhat augments explainability, if I may, right? So when you add a human in the loop, what happens is you can provide specific supervision to the agent saying, well, this is correct and this is wrong. And then the amount of explanation you have to do for the agent reduces because there is a human who has taken the decision, and we are, better able to trust humans than we are able to trust, let's say, a neural network or something of that sort. So while the human might not directly provide any explanation of the agent, it certainly does help in making the model slightly more explainable because, well, you can say the human supervised it in such and such locations where it was, behaving in a slightly fishy manner. Right? So I hope that's good for the first question. And the second question he states is, how do attention spots explain the agent's actions? From what I understand, attention spots tell you where the agent was focusing in a given frame, but how do those focus areas relate to the optimal action? Well, the thing is, I'm not talking about whether the action taken by the agent was optimal at that particular point. What I'm trying to explain is whatever action was taken by the trained agent, what was he looking at when that particular action was taken, right? So the attention model is more of a proxy in trying to tell what the trained agent, the one which we are considering, is looking at the observation, right? I do understand that attention is not a foolproof explanation of what agents do, but in some way, as long as you can make sense of what the attention probabilities show you, I think that serves as explanation in some way. Yeah, but your point is valid. It does not directly tell you that the action taken is optimal. But my counter argument to that would be, I'm not trying to explain the optimal action. I'm just trying to explain the action that was taken by the agent itself. So I hope that's good for the second question as well. There's another question by Ravikant. Sir, I hope I can take that as well. We do have time, right?
Yeah, we have quickly. As long as it's not a very long answer, because I can see it can go. It has potential to.
Yeah. So this question is long-winded, right? So that's something that
the answer could be long-winded. Question is very short.
Yes, so something that should be discussed over coffee, I suppose. So Ravikant asks, I heard that you read about subconscious and spirituality. Can we use DRL to prove the existence? I wish we could do that, Ravikant, but agents tend to be really stupid about abstract topics like spirituality and subconscious. They do not have the same biases as humans do. The problem is the power of imagination that humans have. Agents lack that because we never, imbibe those in neural networks and such. But if something like that happens in the future, I'll be really happy to, invest in it or read about it. Yeah. Do get in touch with me if you want to go deeper into this topic.
Yeah, thanks. Thanks, Nishant, and thanks, Ravi. So maybe this will if it is not already, maybe one outcome of this workshop could be a new field of RL, working on subconscious spirituality and consciousness and so on. Yeah, thanks for keeping us grounded and on time. Thanks, Nishant. We'll go to the last speaker today, Utsav, who will be talking on Thompson sampling of Utsav is MS scholar in the computer science department, working with Professor Rajkumar. His research interests are in multi-arm bandits, and he's also interested in deep learning models using attention for NLP and vision problems. Over to Utsav, and you have the honor and whatever there may be fortune or whatever of being the last speaker of the thing.
Thank you, Professor, for the introduction. Good afternoon, everyone. So today I'll be talking about my work, which is titled as Thompson sampling approach to linearly constant linked adaption problem. So this work has been done under the guidance of Professor Arun Rajkumar and Professor Lakshmi Narasimhan Tyagarajan. So let's get started. So first few slide, I'll explain what is multi-arm bandit problem. So multi-arm bandit problem is sequential decision problem. So at each time step, we get to see some choices, and the set of choices are fixed, and we need to choose the action, the one choice that has the highest expected reward. So like we can go, so here in this slide, I'm showing there are 3 choices available to us, and once we choose something, it gives one only reward. So reward is either 0 or 1. So suppose we choose time step 1, action number 1, and we get a reward of 1. Then next time step we can choose say action number 2 and get reward of 0. So like this we can go on for till 100 time step. We can randomly explore the choices, And we see that the empirical expected reward, like empirical number of times each arm gave reward. So this one, it has the highest expected reward. So one very basic approach we can do is that we can stop here the random exploration and we can simply commit to this arm. So this has one problem that since everything is random here, so this might not be the best term. So this can be better than this. So to overcome such a problem, a better way to deal with this problem, we have this algorithm known as Thompson sampling. So in Thompson sampling, what they do is, this is a Bayesian approach. So for each arm, they have a beta prior. So we have initialized beta prior between 1 and 1. So beta distribution is basically a continuous distribution whose support is between 0 and 1. So at the starting of this, at time step 1, we sample each beta prior and we see that the expected reward. So sample expected reward is highest for this particular arm. So we select the arm which has the highest expected reward. So we select this and find that we get a +1 beta reward here, and we update our beta prior to this. So this update is done in a way so that the mean of this beta distribution is the empirical average of number of success. So again, we sample from these 3 beta distributions and we see that the second one has the highest expected reward mean. So we choose that and see 0. So again, we update the beta prior here. So like this, we can go on continuing this whole process till unlimited steps. And this doesn't have the problem of the previous thing that where we explore and then we fix on a particular arm. Now I'll slightly change our problem. So suppose we know that we have 3 arms and we know that what is the reward that if we choose a particular arm, what is the reward we will get. But we get this reward if and only if we have a positive reward event. So this is like, you can think of it as some Bernoulli random variable. So if we sample that and see a 1, that is a reward event, and if we sample that and see a 0, it's not a reward event. So we don't get this 0.7 reward in that case. And so the constant we are setting here is that we want certain percentage of total events to be reward events. So there can be many applications of this. So one particularly interesting application is that in multiplayer game, so we want some constant throughput, and in that constant throughput we want to have as high bandwidth as possible. Keeping this application in mind, we can think that, okay, so the way we can have this handle this is that we can output a distribution using which we can select these arms. So this distribution we can think of it as some oracle which is the optimal. This lambda is the optimal distribution, with which if we select these arms, we will meet the constraint as well as we will have the highest expected reward. So as I was saying that, so we can think of each arm as Bernoulli reward event. These are the probability of error for each arm. And now getting into the domain of link rate adaptation. So each arm can be thought of as encoders. So this is encoder 1, this is encoder 2, this is encoder 3. And for each encoder, we can select a particular channel. So this channel is selected by a gamma, which is not under our control. So once we can only select an encoder, and distribution selects the channel for us. We don't know which channel gets selected, and even after transmission of the packet, we don't know which channel was selected. So, so we only see if the transmission was successful or if it was a failure. Now, so in terms of matrix, we can show this, see this. So, so this is our error matrix. So our row here corresponds to one encoder. So this is the reward vector. So this corresponds to reward if there is a successful transmission for encoder 1, and these are kind of probability of error for channel 1 for encoder 1, and this is for channel 2 for encoder 1. And we can see that if we multiply E times gamma, we will get the probability of error for each encoder. And also we have the constraint. So this is the maximum number of error packets we can send out of total packets. So this is the information that we start with. So we have the reward vector and we know the error matrix. We don't know this gamma, and we certainly don't know this, what is the probability of error for a particular encoder. So stating the same thing in some mathematical sense. So this is a linear objective. So this is the expected reward, and this is the constant, linear constant. So we can solve this problem using linear programming, but the only challenge here is that we don't know this gamma. So we can try to get the gamma. So the algorithm that we propose to solve this challenge is that, so suppose at time step n, we have a lambda. We sample from that lambda to select an arm to play. We observe success or failure after choosing that encoder, that arm. And so we have all the history of success and failures till time step n. So we can use that to find the maximum likelihood estimate of gamma. And using that maximum likelihood estimate, we create a Dirichlet prior, from which we sample gamma hat. And using that gamma hat, we simply solve the linear programming problem as stated in the last slide and update lambda. So this is our algorithm. So let's get into the experiment. So I'll discuss the metrics we use to judge the algorithm. So one matrix is regret. So the way regret is formulated here, it is the difference between the maximum reward for like in set of all arms, so maximum available reward, minus the reward that we get in a particular time step. So our problem with this thing is that if we keep on choosing the arm which has the highest reward, that might have a lower regret as compared to choosing using some other distribution. So because this is a linear constraint problem, and this doesn't take into consideration the constant. So a better metric is to use the total reward till time step t divided by the total the cumulative number of violations that it makes. So the experiment parameters that we did is that the error matrix, we created it using convex combination of a full rank matrix and a lower rank matrix. And the gamma that we used was uniform and non-uniform. So we combined various parameters and we conducted our experiments. So here you see the results. So I'll quickly go over the algorithms we compared our result with. So this green one is our algorithm. This red one is actually a pseudo algorithm which we devised to measure how good is our green algorithm. So in the red algorithm, the channel that got selected after transmission of packet, we even know that information. So and this link on TS is earlier best algorithm for this thing. So what they do is that this is a Thompson sampling based algorithm. So they have beta prior where they use that to measure the error, the expected error for a particular arm, and then they solve a linear program to get a lambda. And finally, this blue one is KL. So this is a UCB based algorithm where they use KL divergence to to create a get the UCB term. So as we see that our algorithm has a somewhat higher regret, and their algorithm has a lower regret. This is simply because the number of violations that their algorithm is making is higher than ours. So so the main metric we can see the cumulative reward by violation metric. In that thing, our algorithm is performing much better than Lincoln TS or KLUCB. So, and for this setting, we used a 0.3 convex combination of full rank matrix and 0.7 with 0.7 of a rank 2 matrix, and the gamma that was used was non-uniform. So in another setting where we used 0.9 convex combination of 0.9 full rank matrix and 0.1 rank 1 matrix, and uniform gamma, we see that here also our algorithm performs better than like Lincoln TS and LUCB. Even there, our regret is lower than Lincoln TS, and the violation of Lincoln TS is higher than us. So I'll discuss the future directions that can be done. I mean, explored after this. Is that one thing? So we assume that there is some gamma with which the channel gets selected after each time step. So instead of gamma, we can so instead of a simple distribution, we can model the problem using a Markov chain. And we think that in real world, that is the better better modeling, because simply in gamma you can skip from channel 1 to channel 5 at a single instant, but in real world the transmission is a bit slower than that. Another thing that is still pending is that we can obtain a theoretical regret and violation guarantees for this algorithm. So the challenge here is that there is this linear programming with which the arms interact with each other. Like to get the lambda, you have to solve the linear programming. So it's so there's that challenge. And one more practical consideration is that we can try to speed up the MLE process, maximum likelihood estimation process. So currently there is no, I mean, the MLE is not closed form. So we need to do projected gradient descent to get to find the gamma. So that takes a bit of time, and we can try to get see if there is some better initialization or anything that we can do to speed up the whole process. I thank everyone to attend the talk, and if there is any question, we can discuss now.
Thanks, Utsav, for the talk, and also for getting us back on time. Let's see whether there are any questions from the audience. I encourage you, all the audience members, to use the chat box or the Q&A. Utsav, I just have one question. In that optimization for the LP problem that you showed, where you want to optimize, maximize and minimize a linear function subject to constraints. You said something is unknown. What was unknown? The gamma value was unknown, or the expected value of gamma was unknown, or the distribution itself was unknown?
The distribution itself, we don't know. The distribution that is used to select the channel, we don't know that.
Okay, the distribution itself is unknown. What have you thought about? There are these methods which, if you have some more information, some which work with like using the generalization of Chebyshev inequalities, which are distribution-free inequalities. So have you looked at some of those ideas?
I am not so familiar with them, but I'll explore them after.
So you can have access to Boyd's book on convex optimization. So they solve some problems where you again optimize where the distribution itself is unknown, but you have some other information. So you try to overall, let's say you have some mean and the variance is observed, but you don't confine yourself to some distribution. You want to solve some problem over all distributions, and they formulate and solve LPs, which end up becoming convex problems, conic problems.
Okay. Yes, I'll explore them after.
Just some food for thought.
Yes, sir. Thank you, sir.
Any other questions for Utsav or any of the earlier speakers? If they're still here, you can raise in the Q&A box. They would be, I'm sure they'd be very only too glad to answer the answer. Yeah, if not, let's start. It's my present duty to thank all the speakers, Professor Ravindran, Ramya, Nishant, Saarthak, and Utsav for the talks. And I'm at the risk of sounding narcissistic, I'm glad that all the talks have come together in a very nice, cogent theme of reinforcement learning. I work in control and has always been trying to get some more insights into RL, and this is a good crash course and it's given me lots of ideas. So students who approach me for these are nice projects with the problems which I think can be which can be taken up in future. I also thank our colleagues and friends from RBCDSAI, Martina, Sintamiran, Sridhar, and others who have worked to put this thing together. And hopefully the next workshop will be physical. And I also realize that there are several people who are joining in remotely. We will try to see whether we can have at least the people within campus attending physically, and the others whether we'll be able to accommodate them virtually and remotely. And I should also, before I spoke to the students, the first people that I contacted were their advisors, Nandan, Ravi, Neerav, and Arun Rajkumar, and all thanks to them also for suggesting the students and their names and the topics. And with this, we'll conclude. So there's been a lot of food for thought, and now this is a joke that I keep repeating several times. Now it's nearly lunchtime. Food for the stomach, the pet puja. Thanks, and looking forward to seeing all of you at the next RBC event, either in person or virtually.